시간이 된 관계로 제7차 2024년도 BrainLink X-Lab Day Talk 콘서트 시작하도록 되었습니다. 저는 이번에 7번째 BrainLink Talk 콘서트를 주관하게 된 부산대학교 최윤석이라고 합니다. 반갑습니다. 자, 오늘 프로그램은 한 분씩 오늘 총 7분의 해외 전문가님들을 모셨는데 한 분에 한 20분씩 해서 여기 여러분들 브로셔에 나눠드렸듯이 톡을 들으시고 마지막에 Q&A 세션은 모든 분들이 발표를 끝나시고 나서 Q&A 세션을 같이 가지면서 패널 토론도 같이 가질 수 있도록 이렇게 시작하도록 하겠습니다. Alright, welcome everyone. Welcome to the 7th 2004 BrainLink X-Lab Day Talk Concert. Okay, so especially this talk concert where is entitled Advanced Technologies for Next Generation Aerospace Systems, Materials, Manufacturing, and Process Standardization and Certification. So we just, we have 7 distinguished international speakers here. I'm sorry, actually, we have about 10 minutes left. BrainLink X-Lab Day introduction video. Okay, this is.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X-Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X-Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. BrainLink X-Lab Day establishes a global science and technology network among overseas scholars and Korean researchers. And in 2022 and 2023, a total of 24 BrainLink X-Lab Day sessions were held in each technical field, with 787 participants, including 161 from overseas and 626 from Korea, building a global human network. Also, talk concerts, one-day public seminars, were held in collaboration with the 2 nights and 3 days of BrainLink X-Lab Day to enrich their experience. Professor Luke Pyeong-se Lee of Harvard Medical School, Professor Ji-won Kim of MIT, Professor Andrew Goodwin of University of Oxford, Emeritus Professor Teruo Okano of Tokyo Women's Medical University, Jeffrey Newmark of NASA Goddard Space Flight Center Research Astrophysics, and Professor Dan I. Anderson of Uppsala University. The discussions will span 12 national strategic technology fields, pivotal to Korea's advancement, including the 3 game changers: quantum mechanics, nuclear technology, and AI. The event will see the participation of 40 Korean and international scientists and engineers, with 2 organizers leading each technical segment The gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. And talk concerts will be held in collaboration with all BrainLink XLab Day sessions. The focus of XLab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each XLab Day session to ensure ongoing dialogue among attendees and promote collaborative research. COAST supports the reinforcement and expansion of the networks established through XLab Day. COAST, the organizer of XLab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the Fourth Industrial Revolution, where science and technology spearhead groundbreaking challenges, COAST remains dedicated to its role as a facilitator of scientific and technological innovations.
안녕하십니까. 한국과학기술단체 총연합회 회장 이태식입니다. 과총은 사회 참여 확대와 권익 신장을 도모하기 위해서 1966년 설립한 공익법인으로서 과학기술단체 육성 지원과 다양한 정책 연구, 기획, 조사, 자문을 통해 과학기술 발전에 기여하고 있습니다. 저는 2023년 과총회장으로 취임하여 새로운 도약을 위한 비전, 프라이드 코스를 선언하였으며 이를 실현하기 위한 운영 목표와 추진 전략을 중심으로 빛나는 100년을 향해 모든 역량을 집중해 나가고 있습니다. 더 나아가 우리나라가 미래 핵심 기술 분야를 선도하는 기술 주권 국가로 자리매김하도록 국가적인 원팀 플레이를 이루는 데 있어 강력한 조력자가 되겠습니다. 대단히 감사합니다.
BrainLink XLab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making XLab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink XLab Day.
All right, so we shall start by the first talk, which is additive manufacturing industry trend, will be given by Dr. Brent Stucker, who is Chief Technological Strategist for Hollers Association. Please welcome Dr. Stucker.
All right, I'm excited to be here today and look forward to sharing with you some of what I do with Wohlers Associates. If you're not familiar with Wohlers, it's part of ASTM International now. So ASTM is a standards committee where we do most of the standards in the additive manufacturing industry are out of there. And a few years ago, they bought Wohlers Associates, which is a market intelligence company. And so I work with them part of my time as chief technology strategist. And so a lot of what I'm going to talk about today as far as market trends and all of the facts comes from the market intelligence that Wohlers gets, and but all of the sort of conclusions and some of the sort of future things that we'll talk about are actually just my opinion, so not necessarily the opinion of ASTM. So let's start out. If we're thinking about additive manufacturing or 3D printing, a lot of people say, how big has it gotten? And we estimate that really this last year, 2023, the additive manufacturing market grew to about $20 billion. And so that includes machines, it includes materials, it includes some services like maybe training or servicing a machine to keep it in good repair. And if you look at the growth trends on the right, that's 11% over 2022. So historically, over the last 30 years or 35 years, additive manufacturing has grown at a rate of more than 25% per year. The last year wasn't that great. It was only about half as fast a growth, but still, that's pretty good growth when you consider established industries. But the another thing I want to draw your attention to here is additive manufacturing is only 0.13% of what is the massive manufacturing market worldwide of over $15 trillion. And so really for additive manufacturing to grow a lot, it just needs to eat a little bit more of that, from going from 0.13% to even 1% of global manufacturing would be a huge growth for us. But if we want to think a little bit about the distribution of additive manufacturing, here's an easy way to look at this. So if we chart what's going on in different countries, and on the bottom axis is the gross domestic product of the country. So that's how big their economy is, basically. And on the left-hand side, the number of industrial AM systems that they have installed over the last 20 plus years of the Wohlers report, and adding that all up, what you see is the United States is the highest. It still continues to have the highest install base, followed now by China, which has caught up. Germany and Japan are right there, Italy and South Korea. So you'll look at those and say, wow, South Korea is not so bad. But when you say this by GDP and say if you rate the size of AM installations by GDP and you make bigger bubbles, if you have a higher ratio, South Korea is actually one of the highest penetrations of additive manufacturing in the world when you scale that by GDP. So in reality, South Korea is not doing so bad. It doesn't have nearly as many machines as China or the US, but relative to the size of its economy, you're one of the leading countries in the world with additive manufacturing today. Now, let's take a look at a couple other things. This chart, want to first pull your attention to industrial systems sold. What does that mean, industrial systems sold here? That means additive manufacturing systems that cost more than $5,000 US. So the really cheap little 3D printers, they don't get counted in this number, but just about everything that you would use in an engineering environment does. And you'll notice that in 2023, we had a drop, 12.9%. That's pretty bad, for the machine manufacturers. We're going to talk about what that did to them financially in a minute. But if you look over the last 33 years, we had over 25% growth, averaged out. Even the last 4 years, we were positive, but not very positive, because those last 4 years include some big turmoil from COVID, and then this last year, which was a bit of a drop. So you can see that trend there on the bottom right. But I also want to pull your attention to these upper two right circles here. So if you look just at 2023, which is this left circle, you'll see that Asia Pacific is now accounts for 25% of the machines sold in the world come out of the Asia Pacific. Most of those come from China. The US is still producing almost 40% of the world's machines. You'll see Israel there at 11%. Why is Israel? Well, that's where the headquarters of Stratasys is, and Nano Dimension and these other companies are headquartered in Israel. So they get counted. And then Europe is a little bit lower than Asia Pacific. You compare that back to the older trends where the US used to dominate on the right. Almost 50% of the machines sold in the world came from the United States in that whole range of 1988 to 2023. So what you're seeing is this most recent year illustrates what's become a pretty big shift, where Europe, and particularly Asia Pacific, is actually producing a larger and larger fraction of the world's additive manufactured equipment. Well, a bright spot in that is, even though overall machine sales went down, metal machines are actually selling very, very well. This is a bright spot in our industry. And last year, we through all of our surveys, we projected that there was a 25% growth in the number of metal machines sold, and that the average selling price was somewhere around $500,000 US. So you can see that that's a pretty fast growing, very lucrative area to be in, is in this metal additive manufacturing space. And so that's a bright spot in what was an otherwise pretty bad year last year for additive manufacturing machine sales. If we think about a little bit some other data here and look at material sales in additive manufacturing, what's going on there? That continues to go up and up, because the more your install base, even if you're not growing your install base as fast, as long as they're using those machines, then they have to consume materials. So materials continue to be a strong area to think about for research, to think about for building businesses and whatnot. And if you think about what are the various amounts of material that are sold, so you've got polymer powders still tend to dominate. That's like polymer laser sintering primarily. And then you've got filaments here for things like material extrusion, FDM type processes. You've got photopolymers, and metals are about the same now. And so we have a pretty healthy mix of a lot of different materials out there. What's interesting to me is that the polymer powders, it's an area you don't hear a lot about in the research community. Because people tend to just use a lot of nylon. But there is an opportunity. There's a lot of material goes through there, through all of these polymer laser sintering machines or these multi-jet fusion machines from HP. It continues to be an area where we need some more innovation, and there's actually money to be made. There's quite a bit of money being bought on polymer powders, not a lot of innovation going on in that area. Next, I'd like to talk for a second about how are people then using all these parts that they've been making on these additive manufacturing machines or 3D printing machines. Well, you'll see the biggest category is now end-use parts. They're actually producing components that are going into aircraft, that are going into automobiles, that are going into satellites, that are going into shoes or whatever, or dental. Well, the dental ones usually are mold, but hearing aids. And so what you find is that end-use parts are now almost a third. But if you combine that with metal tooling, patterns, and jigs and fixtures, you see all of those applications, you're actually producing the thing you want. You're not using it as a pattern or a prototype. And so over the last couple of years, what 3D printing initially was primarily used for prototyping and getting the right shape and seeing how it looked and felt. We've shifted as an industry where the majority of our revenue is now producing a finished good that we want to use. Mostly we use it for the part, but sometimes we use it as a mold or a fixture. And so it's been a pretty major shift, actually. That shift occurred right about during COVID, where we went from more prototyping to less prototyping just in the last few years. And so if we look at, well, how big is that as a market and how fast is that growing, you'll see here how fast that growth of end-use parts has been consistently above 20% for the last, what is that? Almost 20 years, 15 years. And so it's continuing to be a growing area where less and less of what we're doing in additive manufacturing is as a prototype and more growing to use things as a real part. And just to give you a little bit of where are we getting this data, we send out a bunch of surveys and work with a lot of service providers. So we had over 113 different service providers. Service providers mostly build parts for other people. They buy additive manufacturing machines and they make parts. And we had over 115 system manufacturers respond to the survey. That's kind of where we get our data, as a collection of that kind of information. Moving on a little bit. One area that we're talking about then this week is aerospace. And so aerospace has continued to be a growing area almost every year. You can see a little blip, a little jog up there in the 2020s through 2023. So this is aerospace revenue by parts sold. This is parts, materials, and systems and software sold to aerospace companies. This does not include the value of parts made by those aerospace companies themselves, which probably is about the same amount again. So if you think about how fast has aerospace been growing in additive manufacturing, definitely we're well over $3 billion of impact. And if you think about the value, like if there's a lot of you may know about GE is making their fuel nozzles with metal additive manufacturing. You think about the value of those fuel nozzles and how much value that adds to their engines. We're talking about billions of dollars of economic impact when you consider all of the impact of these parts. So this kind of undersells the value of parts in additive manufacturing. So let's talk a brief minute about what's kind of not going well in the industry. And this is a chart I want to talk you through for a second. So if you look at this blue line, this represents the total unit sales of industrial machines on this axis. You can see we've grown in 2014 from, I don't know, somewhere around 13,000 machines sold to in 2023, we're up close to 25,000, right? We had a bit of a fall, as we talked about in that earlier slide there. But what you've seen is the number of manufacturers of machines grew faster than the number of machines sold. Well, most of these manufacturers, if you think about starting a new manufacturing company, you're mostly starting it with debt, right? You borrow money, you start a company, now I got to make money. But if you think about if the number of manufacturers is growing faster than the number of machines that those manufacturers sell, on average, they're making less and less money per year, right? So something's got to give. And what you find is that a lot of these companies were very highly leveraged on debt. And when interest rates went up around the world in the last few years, this has caused havoc on our machine manufacturers. And so this is where a lot of the stress in the industry has come out over the last couple of years, and why we're also seeing a lot of collapse of stock prices as a result. So if we go to an analysis of stock prices that I did, I just updated this last week. And so let's take a look at this. So if you've been involved in the additive manufacturing industry for very long, you'll recognize a lot of these names on the left-hand side. 3D Systems and Stratasys are some of the biggest machine makers in the world. Materialize makes software. Desktop Metal makes machines. Nano Dimension, Velo make machines. Proto Labs makes parts. And then again, Markforged makes machines. So what you're going to see is that at some point in time, they were all worth billions and billions of dollars. People really thought, anywhere from 2021, some of them, the top two, 2014 was their highest market cap ever. Like that's a whole 10 years ago, right? That people hyped that. So this illustrates we've been through two big stock market hype cycles. The really old companies went through their peak 10 years ago. The newer companies went through it the last 3 or 4 years. So if you compare how much revenue they made, so this is revenue, this is not profit. This is just how much money they made selling machines. Most of these all lost money as well, but that was their revenue. And you compare that to their current market value, what you see is that they're pretty close. Right now, the market is saying, wow, we're only going to value these companies at what their current revenue is, or even less. With one exception, you see Nano Dimension there, which is almost 10 times its revenue. You say, well, why is that? Well, they're sitting on more than $500 million of cash. Their market value is actually less than the amount of cash they have. And so people are actually pessimistic when you think about investment. So why are people so pessimistic? It's because of this chart, right? There's too many manufacturers, not enough machines being sold. Some of them have to go bankrupt. We don't know which ones are going to go bankrupt or get bought. So now we're just going to lower the price on everybody. That's kind of what's happening in the industry. And so this is an important trend. And you can see for those of you or people in the world who put a lot of money in these hypes, they've lost almost all of their money, right? They only have pennies left per dollar on their investment. So But nevertheless, and again, I want to say this doesn't include the stock prices of major people in our industry like Nikon, GE, and HP, because their additive division is a very small part of their global footprint, and therefore it doesn't really affect their stock price very much. So it doesn't make sense to kind of show them this. So I just thought I'd throw out these sort of trends as food for thought, helping us have a good discussion here at the end of this talk concert and throughout the week for those of us who are involved. And I'll leave us with a quick, where do we think this is going at Wohlers Associates? You know, when you look at the trends and you say, where are we going? Where will we be in 10 years? We're projecting that the industry will get close to $100 billion, over $90 billion in 10 years. And even at that growth rate, if the amount of manufacturers keep going up like it has been, they're not going to be profitable. I mean, there's a lot of money in the industry. So the main thing is, how do you be the ones who are making money and not the ones who are losing money? Because even though a lot of money is changing hands, most people are not making money in this industry. So I'll end with saying we at Wohlers would love, to know what you're interested in as far as market intelligence. If you're interested in taking a short survey for us, then you can scan that QR code, and we'd love to know who you are and how we can tailor our market intelligence to create things that you want to see more of. And so I think at this time, we're not going to take any questions right now. We're going to have a discussion at the end. So thank you for your time.
Right, thank you, Dr. Stucker. It's quite surprising to see the market share for additive manufacturing over the entire year. So after 10 years, we're still under 1%. Ouch. All right, so let me move on to the next talk. Okay, so next talk will be given by Dr. David Rosen. The talk title is Design for Additive Manufacturing Research Frontier. Dr. David Rosen is a principal scientist in the A-Star Singapore. So please welcome Dr. Rosen.
Good afternoon, everyone, and thanks for the opportunity to speak in front of you. Right, so I'm at A-Star, which is like the National Labs of Singapore. Before I joined A-Star 2 years ago, I was a professor at Georgia Tech in the U.S. And just a little bit of an introduction. Like I said, A-Star is about the National Lab in Singapore. There are 18 different institutes in A-Star, everything from engineering, modeling, and simulation to additive manufacturing to AI, medicine, biology, genetics, skin research, things like that. And about 4,500 people work at A-Star on the technical side, so engineers and scientists, in a country that has 6 million people. And I'm part of 2 of the 18 institutes, IHPC and SimTech. All right, so I'm going to talk about design for additive manufacturing. We're going to shift topics from Dr. Stucker's talk. This is one of my favorite topics. It's what I do day to day. And in particular, we'll kind of give a broad introduction to design for additive, contrast that with design for manufacturing more generally. And then I talk about 4 topics that I think kind of represent the frontier of what people are trying to do on the design side in terms of additive manufacturing. So we'll cover each one of these things, but kind of as an introduction, right? Design for manufacturing. When you say that, at least in my mind, I think about tweaking dimensions, adding rounds and fillets, and if you're doing injection molding, draft angles, things like that, you're tweaking shape details. And I think if that's your approach to using additive manufacturing, then you're coming at it from a wrong perspective. You got to be thinking of, all right, so what are the unique capabilities of additive and how can I take advantage of them? How can I design really novel, clever, innovative kinds of designs that push the envelope, that represent things you can't do using machining, injection molding, die casting, things like that. So it's all about the exploiting opportunity and not just focusing on details. So I tend to, again, say we want to take advantage of the unique capabilities of additive. And we need to integrate a lot of different technologies, technology ideas, process ideas, material characteristics, etc. All right, take advantage of the unique capabilities. So what are they? Well, of course, we can make just about any shape. So shape complexity is the big one here. With additive, you fabricate parts layer by layer, adding and processing material like that. Lasers, if you're using lasers, the laser doesn't care what pattern it's tracing. If you're using an FDM or a material extrusion kind of printer, the nozzle, the extrusion head doesn't really care what kind of pattern you're putting there. So you can make just about any shape. And because you can do that, you can also make custom shapes. So hearing aids, aligners, dental aligners, dentures, things like that, they can be custom fitted to the particular patient. So shape can be customized, so can material composition in a lot of cases. So material complexity is also possible. Hierarchical complexity is related to shape complexity. Think of adding tiny little fins or texture to lattice structure to promote heat transfer, for example. And then finally, functional complexity. In a lot of cases, we can make mechanisms, we can make assemblies right in the machine without post-fabrication assembly. A lot of times we can insert metal components or other kind of components into the vat or into the powder bed or into the part as you're building it to make functional devices. All right, so we want to be able to take advantage of that. Dr. Stucker mentioned fuel nozzles of GE engines. There's a picture of one of those. At least that's the picture that GE gives us. Not sure if that's, never mind. So complex geometries, we can see that's a spinal implant right in the middle. Stryker makes hundreds of thousands of those per year and implants them in people. Hearing aid shells, dental aligners. You can actually buy American football helmets with vat photopolymerization fabricated foams like that, and those are also custom fitted to the individual player. So we see a lot of examples of complex geometry, custom geometry, making designing parts that you can't easily fabricate using conventional technologies. I like to wrap all this up into some opportunities and some consequences of those opportunities. So again, complex geometry, custom geometry, multiple materials, no tooling, things like that. So complex geometry, custom geometry, we can do both part consolidation. That's one of the real successes of the fuel nozzle from GE. You integrate 19 or 20 parts into one. You save tremendous assembly and welding and brazing costs. I'll move on a little bit quicker here, but you can see a lot of the advantages here. No tooling one basically means that enables distributed fabrication, distributed manufacturing. If you don't have to invest in a lot of hard tooling in a factory floor, you can pretty much start manufacturing wherever you want. All right. Okay, so let me just go there. When you talk about design for additive manufacturing, if you've been kind of active in this area, you probably have heard about generative design. So generative design is largely offered by Autodesk and the other major CAD vendors, and it's sort of topology optimization generalized. Right? And the technology, you start by defining sort of this design space, and then like a finite element model, you add boundary and loading conditions and things like that. And then the system will go off and generate dozens or hundreds of design solutions, evaluate them, and can present them to you in a variety of different ways. And you as the designer can then kind of explore what that design space looks like. identify a few that you want to go further with, and then ultimately settle on one, and then do additional engineering work to come up with your final design. This is a really good example of taking advantage of the shape complexity capabilities of additive, but it's only one sort of approach here. All right. So let me move on and talk about the first of the topics that I think represent kind of the frontier, which is this whole idea of a manufacturing process chain, not a single manufacturing process, and the need to design for that manufacturing process chain. So in metal additive in particular, you make a part, and for metal powder bed fusion, this is what the part looks like on the build platform with all the other test specimens that you build along with it. Okay? That's not the final part. The final part, this is in this case, hydraulic manifold. You've got to interface that with standard hydraulic components. There's a heat treatment. You need to remove the support structure, remove the part from the build platform, do finished machining, probably do bead blasting. There's a whole series of manufacturing processes that you do. So designing for the first process isn't really sufficient, because the characteristics of your final part are going to be influenced by all the other manufacturing processes along the way. So you want to design for additive, you got to design for the whole process chain. And coming up with a process chain, to some extent, it's pretty straightforward, but there can be a lot of variations here as well. Some cases you may need additional finishing operations or something additional. In some cases you may not. So there's a lot of engineering that goes on there. From a design for additive standpoint, again, you need to design for not just the final part characteristics, but really understand what each and every process does to that in-process part, and make sure that you're designing the part and designing the process to give you the characteristics that you want and need. So what I'm illustrating here is the formulation of a multi-objective design optimization problem, and decomposing that overall problem, designed for the process chain, into subsystems, where one subsystem represents the part, and all the other subsystems represent the major processes that have to be applied to that part. So you design the part, but you also have to design the powder bed fusion process to make that part, so you get the right mechanical properties that you want. But then you do heat treatment to adjust those mechanical properties and try to get more of a homogeneous distribution. So remove supports, do finished machining, etc. Each of these processes has to be designed, and you can't compromise functional performance. Okay, so we've done a few studies along these lines, and I'll just say that this is one example that we did. It's an automotive connecting rod, and it just shows our sort of approach at what some kind of generative design would look like for the connecting rod, just in the sense that we've defined a design space that's, again, part characteristics as well as process characteristics, and designing those processes. And different points in our design space represent considerably different kinds of designs. They all satisfy the requirements, at least to some extent, but depending on your preferences, do I prefer something really strong and stiff, or do I prefer something lighter weight but less stiff? You kind of get different solutions. All right, so we can formulate and solve those big multidisciplinary design optimization problems, and explore the design space and help people understand what the trade-offs are between these different processes and the functional requirements. Product architecture design. So here's another example from the aerospace industry. Another example from GE as well. So here's the conventional designed turboprop engine, and here's an engine that GE redesigned to make the most use of metal additive that they can. What they claim is that they went from about 850 conventionally manufactured parts down to 11. Now, I see more than 11 parts there, but I think it's the main structures and things like that count as the 11. So it's a tremendous part consolidation, right? fabricating far, far fewer parts. Parts are each going to be much more complex, and that has a huge impact on the factory floor, has a huge impact on the supply base, and greatly simplifies the factory floor. Plus, you get reduced fuel burn, so better economy, more power, etc. So there's lots and lots of advantages. But you don't get there. You don't make that change by, again, tweaking some dimensions or tweaking designs. You do it by doing clean sheet design. By really, let's never mind how we've designed and developed engines, what they've looked like in the past. We need to totally rethink these things. Here's another example. This is an electric motorcycle that is plastic. It's plastic printed on material extrusion machines, in fact. And this is another example of totally rethinking product architecture. And when I talk about product architecture, what I'm talking about is really it's the physical layout and construction of the product, and how basically the function or the functions of that product get mapped to those different modules and assemblies. Okay, and so I'm just listing out some of the main functions here. Of course, it's an electric motorcycle, right? So we do get some change right there, right? We need a battery, not a fuel tank, not a gas tank. But also, you don't need a transmission. You have basically a servo motor controller be your transmission. But also, another thing that you'll notice is there are no separate suspension components. So a typical suspension on a motorcycle is shock absorbers and springs and things like that. But the whole structure deforms, and there's also a bumper underneath the seat, and the seat is an elastomer material that's printed and things like that. So, and that's just sort of an obvious, I guess not so obvious in terms of this overall suspension, but certainly with a polymer frame, there will be some compliance there. But the point is that you can think methodically about the functions and about how you're going to divide up the geometry into different components, into different subsystems, etc., and look for opportunities to do function sharing and function integration. Right? Function integration. Hey, if we can eliminate what the transmission does, right? We eliminate the transmission. We save a lot in terms of simplifying the overall product architecture. So we won't go through the details, just this notion that, just because something has looked like the motorcycle on the left for 100 years doesn't mean that motorcycles have to look like that. And in fact, I guess in the context of design for additive, I should have said that that electric bike consists of, I think, 13 or 14 3D printed parts. That's it, including the tires, the wheels, the seat, and the frame. All right, so tremendous change in product architecture. And then, assuming I still have some time, the last thing I'll talk about real quickly is 4D printing. I think this is a really interesting area, a lot of possibilities. Still, it's very early in the technology development cycle. And 4D printing is basically using the shape memory effect. The fourth dimension, of course, is time. So the shape changes over time. Right? So in the shape memory effect, a lot of times you use heat as a stimulus. So you have a part at room temperature, it has one shape. You heat it up, it changes shape. All right. So an example of that, two examples of that are shown here. These parts are being, or a product is being put into a hot water bath. The hot water bath stimulates that shape change, basically. And in one case, the part folds up from a flat printed part into a box. In the other shape, the scissor mechanisms are the actuators. The plastic white scissor mechanisms around the periphery are the actuators, and they open up that solar panel deployment mechanism and unfold the origami solar panel constructions. And so again, that's 3D printing in a nutshell, right? You can print in one shape and deploy in a different shape, have things go back and forth. What are the design opportunities? Okay. So in my mind, this is kind of the big picture, right? These are essentially solid state actuators, right? You can print them, and they can power mechanisms that deploy, that change shape, etc. How do you implement those sorts of functionalities conventional? Well, they're called mechatronic systems, right? Use a lot of servo motors, servo motor controllers, a lot of sensors, a lot of shafts and bushings and bearings and washers and fasteners and things like that. And many of those components can be eliminated if you can design good shape memory actuators. And that's, I won't go through all the details there, but that is kind of the story there. And so we now have a new project at A-Star in Singapore on 4D printing, and a big part of that is designed for 4D printing. And the idea is to try to make progress toward that idea that I presented on the previous slide, which is to use the shape memory effect to try to develop actuators for systems that deploy and change shape. And so we can think about all these different components that people have developed over the years, and then put those components together in novel ways to do very kind of different deployment and morphing or shape change kind of activities. So up on the top there is just something that deploys, it extends, it bends, and then down here is an origami construct that changes shape, just to give you an idea that you can get a lot of different kinds of constructs here, put them together in different ways, and achieve functionalities that really haven't explored before, haven't had the ability to explore them. So I'll just wrap up here. Summary, I wanted to introduce this notion of design for additive manufacturing as an opportunistic design process, not just this kind of constrained, restrictive process of tweaking things. Designing for the additive manufacturing process chain is a very important consideration. And there are good ways to set up that process chain or establish the process chain and then design the part and the product for it. I talked about rethinking product architectures, essentially, thinking of new ways of organizing the way products are built and thought of. And then finally, I introduced design for 4D printing. Tried to identify some challenges and opportunities in each of those areas. Hope you found that interesting, and that'll conclude my talk. So thank you for your attention.
All right, it seems like a design for additive manufacturing is kind of a very comprehensive system integration is required than you think. All right, so we are going to move on to next talk, which is will be given by Professor Sheng-Min Guo, professor of Louisiana State University. So he's going to talk about the material selection and additive manufacturing for gas turbine engines. Please welcome Professor Guo.
Thank you. So today I will talk about the material selection, additive manufacturing, and temperature control for turbine and rocket engines. And take a look at that's the picture of a Rolls-Royce turbofan jet engine. You will find 3 shafts, and it looks very complicated design. You have to select the materials properly to meet the need. For example, take a look at the front section of the turbofan. You want a very lightweight and high-strength material. Typically, it's made of a composite or titanium honeycomb structure. However, when you move to the center of the jet engine, in the combustor, in the turbine section, where the temperature is so high, normal material typically will not be able to withstand that kind of working temperature. You burn, let's see, hydrocarbon fuel with air, the burning temperature can be as high as maybe 2000 degrees C. Ask yourself, what kind of material you can use to withstand that kind of a working temperature. For aerospace application, therefore, it's very important we need to consider both material design, consider the fabrication and the thermofluid, the cooling technique. So typically, for the high pressure turbine blade, you can see it right here. There are several technologies. Material development, that's one thing. Over the years, we have the development of the super alloys, and now you can find a single crystal blade. The entire blade are made of single crystal, nickel-based super alloys. But even with nickel-based super alloy material, it will not be able to survive under jet engine working condition because the temperature is so high. Nickel-based super alloy single crystal will melt, will lose mechanical strength very quickly. So what you will find, in order to safeguard jet engine components, you have to add, let's see, on the surface, add a ceramic layer to provide a so-called thermobaric coating. And inside, we have to think of introducing cooling jet, using cooling gas to provide cooling to make sure that all the engine hardware, you don't exceed allowed temperature. The nickel-based super alloy, even the single crystal one, the maximum temperature probably is less than 1,000 degrees C. 1,000 degrees C apparently is not hot enough to operate a jet engine. So the idea is near the wall, you make sure the temperature is at or below 1,000 degrees C. Away from the wall, you want the temperature as high as possible. Jet engine components are made of those expensive material, very expensive. At the moment, you may find the 3D metal-based 3D printing people are talking about to do the repair work. I really don't see the immediate application of using 3D printing to fabricate the entire high-pressure turbine blades, because the turbine blades, you have to make sure the growth of the grain along certain direction give you the maximum strength. For temperature control, that's something I want to talk about. I want to find out what's the temperature distribution in the engineering part we are going to fabricate, including 3D printed parts. In order to find the temperature distribution, you need to understand the flow condition. For example, for the engine components, find out what is the hot gas temperature, find out what is the heat transfer coefficient for the high-speed flow around the jet engine components. You also need to know inside the cooling gas, what's the pressure, what's the temperature, what's the heat transfer coefficient, etc. Is that enough? No. We still need additional information. We need to find out what's the thermal property of the material you're going to use to form the jet engine components. Let's say the engine blade. The engine blade is made of nickel-based superalloy. What's the thermal diffusivity, thermal conductivity, those basic thermal properties. And on the surface of the nickel-based superalloy will be coated with a ceramic layer. Let's say it should stabilize the cornea. And then that's a question, what's the thermal properties for those ceramic layers? Therefore, you have to understand all those thermal properties enable you to predict what's the final temperature distribution inside a very simple, I'm saying very simple, jet engine, let's say first stage nozzle guide van, or the first stage turbine blade. Talking about the fabrication, because here the topic today is on the materials, additive manufacturing, and the thermal properties. For metal-based additive manufacturing, laser powder bed on the left-hand side and the direct energy deposition on the right-hand side are very common fabrication technologies. And in fact, I have long-term collaboration with NASA. Look at all those components NASA already fabricated using additive manufacturing for the propulsion application, right? You see the nozzles, and NASA did a fire test. I assume, look at the color, you will know the temperature probably over 1,200 degrees C. Just look at the color of the material. Ask yourself, what material to use to fabricate it, and how are you going to safeguard your entire rocket engine operate under such high temperature, under such high load. For the last few years, I tested different 3D printed materials supplied by NASA. We wrote a book together several years back. That's a book called Metal Additive Manufacturing for Propulsion Applications. And my group contributed to the thermal property measurements you will find in the appendix of that book. So just to show you a list of materials we tested, pretty much every single material NASA applied additive manufacturing, they send the material to my lab. We will find out what's the thermal conductivity, thermal diffusivity as a function of temperature. We are going to test those 3D printed materials, thermal properties, all the way to the working temperature, not just from room temperature. Once you know that, you can go ahead, try to do the simulation to find out whether your design can meet your need. And for the first three items listed in the table here, it's a GR Corp. That's a copper alloys. That's something I want to spend a little bit more time to discuss. Very strange. Look at the rocket engine combustor and the nozzle. Look at the right-hand side. That's a 3D printed rocket engine nozzle. Rocket engine nozzle, inside the combustor, you burn the fuel with air, let's say hydrogen, react with oxygen, will generate a temperature maybe over 2,000 degrees C. What kind of material you are going to use to safeguard the structure of the rocket engine nozzle and the combustor chamber? Definitely, nickel-based super alloy will not be adequate. Nobody was thinking of using tungsten because tungsten is too heavy, and probably tungsten will not survive any oxidation environment. Surprisingly, NASA decided to go for the copper alloy. Using copper, of course, pure copper will not be able to survive the working environment. Design of this new copper alloy is one of the NASA Glenn Center's activities. Glenn Center Copper 42, you have to add some alloy elements, make sure this copper has highest possible thermal conductivity. Why? Look at the right-hand side picture. You see all those little holes 3D printed into this rocket engine nozzle. That's because you pass your fuel, for this case, let's say liquid hydrogen, through those cooling channels. You use a cooling liquid hydrogen to safeguard this very important piece of equipment you just print out using 3D printer, rocket engine nozzle. Because one side, you have a liquid hydrogen sitting at what, minus a degree C, and on the opposite side of the wall, you have maybe 2,000 degrees C. Those large temperature gradient will happen across a very thin layer of material. And the inside of the combustion chamber, you see a pressure, maybe several hundred atmospheric pressure, and the flow running through the nozzle will get accelerated to a higher Mach number in order to generate thrust. So consider all those requirements, you will understand, wow, that's a pretty challenge. We have to find a material to meet those needs. NASA finally figured out that that's a NASA copper alloy, GR Corp 42. They printed out this rocket engine nozzle, actually fire tested. Look at the properties of the copper alloys. You may say, look, that's the conductivity against the working temperature. My contribution in that book published by NASA is obtain all those thermal properties of AM parts working over different temperature range. So look at the pure copper. Yeah, pure copper give you highest thermal conductivity, right? Can stand a chance to take heat away. However, pure copper, they are not strong enough. When you heat up to a slightly elevated temperature, the copper will lose strength. The goal of this NASA copper alloy GR-COP 4284 design is let's find out copper alloys which can give you a good mechanical strength at elevated temperatures. We all know the melting point for copper is around 1000 degrees C. Apparently, nobody can operate because when you get there, the thing will melt, right? The pure copper, when you heat it up, it will become very soft, will not be able to sustain those high pressure inside the combustor. You may say, how about add some elements, alloy elements to make the alloy, make it stronger? Yes, NASA thought about this many, many years ago. For example, the one alloy of copper alloy is 99.8% of pure copper plus maybe 0.1 to 0.2% of zirconia. That sounds a pretty good option, give you good thermal conductivity. However, the mechanical strength is not good enough. On this chart, you will find the recent development of NASA GR-COP 42 and 84, two NASA copper alloys, give us reasonably good thermal conductivity. For example, GR-COP 42 give you conductivity value around 340 watts per meter Kelvin. That's not too far away from 380. That's pure copper, because as I said, pure copper will not give you good mechanical strength as soon as you heat them up. We tested the mechanical strength of GR-COP 42 and 84, two types of copper alloys. The only difference is the concentration of chromium and niobium ratio. For GR-COP 42 means I have around 4% of chromium with 2% of niobium. 84, we have a slightly higher chromium concentration, close to 80% atomic level, and niobium is half, it's 4%. So with this unique composition, the GR-COP alloy can happily operate up to like 700 degrees C. At 700 degrees C, here I didn't show you. At 600, you see the value for the solid line, which is GR-COP 42, give you a mechanical strength over 150 megapascal. And I believe when you heat it up to 700, this alloy, 3D printed alloy, rocket engine components can still have a mechanical strength over 100 megapascal. Due to the selection of a material utilizing the additive manufacturing technology, we can incorporate a very complex cooling design into your parts. So that's the message I want to pass by today. Well, somehow this video won't play. Okay, I guess we want to play. I will stop here. The conclusion is, when you design for additive manufacturing, select your material properly, consider your engineering application, what's the required temperature range, what's the required stress level, and then additive manufacturing will enable you to implement very complex design into your part, including for engineering application, the cooling configurations. Of course, more studies need to be applied to AM parts because you use a new alloy. For example, NASA use GR-COP 42 or 84. They definitely want to find out for the 3D printed part, whether the 3D printing part, they will give you the same mechanical property or thermal property as the parts fabricated by conventional method, let's say using a forging or extrusion method. They want to see the difference because we know the 3D printing, especially laser powder bed and direct energy deposition, will give you very fast cooling rate, give you unique microstructure. Those unique microstructures very likely will impact the thermophysical properties, the thermal conductivity, diffusivity. They are strong function of microstructure. Once you change microstructure, the thermal properties will change as well. Okay. All those work cannot be done without the support of my graduate students. And I just list the names here. I have a pretty large group, over 10 students worked with me on additive manufacturing technique. And also, I would like to thank my sponsor, mainly from NASA and National Science Foundation. Okay, I will stop here. Thank you very much.
All right, so we really feel like the copper is superalloy. So we're going to move on to the next talk, which will be given by Professor Alison Leeds from Pennsylvania State University. The talk title will be Microstructure, Metallurgy, and Mechanics in the Metallurgical Manufacturers. Please welcome Professor Leeds.
Okay, so today I'm going to talk about some of our work related to 3 different ways that we're trying to implement additive manufacturing or enable the implementation of additive manufacturing in structures. So I'll focus on just some snapshots where we're thinking about harnessing in situ signals to predict resultant properties. Then we'll move on to multi-axial stress states and think about how we can design against failure. And then finally shift gears and think about functionally graded materials. So the first part is thinking if we fabricate a component with additive manufacturing, we inherently are trying to impart different complex structures. We have different thermal histories and microstructures and mechanical behaviors within complex components that we fabricate. So the idea is, are there things that we can do can we use in-process signals to be able to assure ourselves that the parts will have the properties that they need to have? So this means, is there something that we can do that we can monitor the process to say, I'm certain that I have the strengths or the ductilities that I need at every location within my component, even though it's heterogeneous, to allow me to have the properties I need. Okay, so the way that we've done this is that we've taken a look at the knobs that we can tune in powder bed fusion, and we've fabricated components in different regions of this process space. So this is a plot of laser power versus scan speed, and the different symbols represent different types of regions that we might be processing in with laser powder bed fusion. Specifically, red would be if we have keyhole mode processing. Blue would be if we enter into beating up thermal conditions. Green is lack of fusion type conditions, and then gray would be, black and gray would be dense. And the idea here is that we would not intentionally process in these different regimes, but depending on the design of our component, we may enter one of these thermal conditions. So we want to understand, are there things that we can do during the process that we could recognize that we've gone into one of these regions? So we fabricated samples with each of these, looking down at a build plate. Each of these tensile samples has a different power and scan speed combination. And in particular, what we're doing is we're monitoring the process during fabrication. So we have photodiode sensors in our build chamber, and we can monitor the intensity of the photodiode at every point in time, as shown by this video here, where the photodiode intensity is shown by the color, and this is scanning a single cross-section of one of those round tensile bars. So what we do is we have then data during processing where we have information of the photodiode intensity of each of those approximately 300 samples, 500 layers of data, and we can use this and we want to say, are there particular signatures in that image that tell us that we're processing something with a low strength or a high strength or ductility? And so just as sort of a baseline, if we take a look at our laser power versus scan speed for photodiode intensity, we can start to see that if as we increase our laser power, of course, our photodiode intensity increases. That's represented by the colors in the top left plot. The size of those represents the standard deviation as you go through the different layers during processing. And the idea here is that if we try to correlate just the photodiode intensity itself with the ductility, which is the vertical axis on the left here, or the ultimate tensile strength, which is the horizontal axis, we don't see a correlation between photodiode signal intensity and the properties, which we didn't expect to see, but we wanted to check that first. So now what we want to do is analyze those signals a little differently. And so we moved to a machine learning and computer vision type framework where we say, okay, let's take a look at the data that we have from each of those samples and each of the layers. And we put those into images as shown here. And we want to pull out the information and try to see if we can find something that tells us whether our properties are good or bad. So we use feature extraction. So we use transfer learning to pull out the features and compress the data from these signals. And again, we have 500 layers of data for each sample. And then we use the compressed data along with our known values for strength and ductility on a subset of our samples to train a regression model. And so what this allows us to do then is I'm showing a bunch of plots here As we go, the top row is our predictions of ultimate tensile strength versus measured, and the bottom is predictions of ductility versus measured. And from left to right, these are just increasing complexities in DCNN architectures. And what you can see here is that the solid line, each of these represents our average predicted ultimate tensile strength or ductility as a function of measured. And the bands represent the scatter because each of those samples has 500 layers of data. And so what we can see here is that we are able to pretty well predict, despite variations in discrete layers, an average strength of our part during processing as well as a ductility. So we could use this then to say we could define a cutoff strength or ductility to say that we want to sort of say this is our value, we want to reevaluate the part. So the idea here is that the first thing that we can do here is we have demonstrated the ability to harness these in situ signals to predict properties. So strength and ductility are shown here, and we've done this for different alloys. The second thing that we've done that this shows us is this has implications for real-time process correction or part certification. So you could be processing a part and collecting these data to understand that in a particular region you have lower strength or ductility than you need for that application, meaning that you need some sort of intervention. Okay, so that was for uniaxial tension, but in actual additive manufacturing, we're interested in complex shaped components. So I'm going to talk about what if we have complex shaped components? How do we predict failure in these parts? And so these are a number of different geometries that we could see, where I'm just going to describe two things to you to kind of get us on the same page in terms of when I say something about stress state. We can define our stress state as our stress triaxiality, which is just the negative pressure of our stress state. So if we have a high stress triaxiality, it's going to want to pull open pores in our sample. And then our normalized load angle parameter theta bar tells us about the second principal stress. It's a little bit convoluted, but it tells us the importance of shear, for example. Okay, so the reason that I bring these up is that if we take a look at, for ductile metals, the amount of ductility that we have, so the vertical axis in this plot, it's a function of those two parameters. So what you see here, okay, I see, this works. So if you have, so for any combination of these two, we can have a very low ductility over here, or we have a higher ductility over here. So the amount, the distance between your bottom plane and this surface, this fracture locus, tells you the amount of ductility in that stress state. So the idea is for additive manufacturing, if we have these complex shaped components that are accessing lots of different stress states here, we want to know how much ductility we have in each of those to know how far we are away from failure. So we do this as a two-step process where we fabricate samples and we first study the plasticity behavior and then the fracture behavior. In both of these cases, we use a number of experiments, we develop models, and we calibrate those models so that we can understand how the material deforms and fails. And I want to highlight a unique piece of equipment that we have in our lab that allows us to probe a wide range of stress states and materials. So this is a custom-built dual actuator test frame, so we can apply any combination of vertical and horizontal load to a sample, which allows us then to look at a wide range of stress states that would be applicable for loading. And I won't talk about the details here, but for plasticity testing, what we can do is we're able to see that we can match our experimental data, which are the points, with a computational model, which are the lines, and we're able to describe how the material initially yields, which is in black, and then how it flows with increased plastic strain, which are the colorful rings after that. So we can put this in a finite element analysis code so that we know how the material deforms. And the next thing then is to say, well, what about how it fails? And so when we think about failure, there's some experimental techniques that we'll apply so that we can understand the failure behavior. So these are some geometries that we look at when we're talking about failure. We want to look at a wide range of stress states again, thinking about what would we see in an additively manufactured component. So in these cases, the red point represents where failure is going to occur under uniaxial tension. This is a out-of-plane hemispherical punch test to get us equibiaxial tension. This is to think about if we have high stress triaxialities, these are round notch tension specimens, and then combined tension shear. And so what we do is we test our material in all of these different stress states, and we measure the ductility that we get. So basically how much plastic strain we had at that red point up until failure. And that allows us to get those fracture loci that I said we were interested in at the beginning. So these are fracture locus for stainless steel, and then Ti 6.4, where we have our ductility as a function of those two parameters I talked to you about. And we can see that for stainless steel, we obviously have a much more ductile material than Ti 6.4. But what we're able to do here is say how much ductility we have in each of those stress states. And I'll show you how we use this in just a moment, but this is for dense materials. So the other thing we wanted to look at is say, well, what about if we have defects? So a big concern would be, okay, if I find a defect in one of my additively manufactured parts, do I need to throw it out, or can I still use it? What are the implications of this? So to study that, we've fabricated samples that have intentional defects within them. So we fabricate tensile samples, for example, with a single pore at the center, with a wide range of sizes, where we're interested in the relative size of that pore. And then we can see how our stress strain curves are impacted by those defects. So we would have our stress strain curve for a dense material in black, and then the different colors and numbers represent if we have increasing pore size, our ductility drops off, and then eventually our strength drops off. And then we said, well, okay, that's for uniaxial tension, but what if we now have something that's really going to accelerate the failure of those pores and rip open those defects? So these are notch tension specimens, which will increase or reduce the ductility further. So if I want to place this in context with what we just spoke about, so we have our 3D fracture locus, strain to failure as a function of those two parameters. And what we're looking at here for these round specimens is just this right-hand side, so load angle parameter of 1. So that's just pulled out here. So we have our ductility versus stress triaxiality. We have increased stress triaxiality, lower ductility. If we now look at adding pores in, we can see that as we add pores in, our fracture strains start to drop. And then also the dependence on stress triaxiality drops as well. So what we can do is we can say, okay, so now we have an understanding that when we have pores of certain sizes, we're reducing our ductility, and we can recalibrate our 3D fracture loci as shown here. So this is showing now what our ductility would be if we had 4 or 16% cross-sectional area loss with a pore. So our ductility drops and our fracture surface flattens out. So how do we use this? So the way that we use this now is if we think about a complex component made by additive manufacturing, we can subject it to certain loads and we can do the finite element analyses to show what our plots of stress and strain would be, but we can't just predict where that's going to fail. We need more information. So we can plot out our stress state as well as every location, and we can go back to now our fracture locus that we just developed. So if we take a look at this blue one, we can say for every point, we have a unique location of our theta bar eta, so we have a different location here, and we have some stress and strain that we've reached. So we want to know how far am I from my fracture surface. And if I'm really far away, we're going to say that damage is 0. If I'm right on that fracture locus where I'm going to fail, damage is 1. So what do those contours look like? So this is what these look like. So we have most of our material is very far away from failure, it's blue, and some of it up here is very close to failure, it's red. So that would tell us in this particular design, we would have to change our design to avoid failure. Depending on whatever safety factor we were interested in, we could adjust our design accordingly. The other thing, though, that we can do with this, and this is the powerful thing, is we can say, well, what if we do have defects in our material? How critical are they? So now we could say, well, I want to assume that I have defects that take up a certain size. So maybe this yellow surface here. And we would say, how far away from that surface am I at every location? And so in this case now we see that there's a few more places that light up in red, meaning that we would be close to failure if we had pores of that size. So this tells us then we can take a look at a material and a design, and we could adjust and say, what are the areas that I really need to inspect for pores and of what size? And then do I need to redesign this material at all to actually use it? So this is the thing about this is now we have this method that allows us to determine the impact of defects and stress state on fracture. So we know the ductility based on these things. And it also gives us a guide for non-destructive part evaluation. So it tells us where we need to look for defects, and it also tells us the criticality of the defects found. And we can flip it to say, what is the critical size of defect I have at every point in my material, and look for that as well. All right, in the last few minutes, I'll talk about functionally graded materials, where in this case, we want to think about putting different properties at different locations within a complex component by changing the chemistry. So this is an example schematic to show, okay, if these colors represented things like thermal conductivity or stiffness or magnetic permeability, we could get different properties at different locations by putting different materials in different locations. So we can use this to join dissimilar metals or tailor properties, and for this we use directed energy deposition and deposit different materials from different hoppers as a function of position. So we've worked in this area for a while, and we were initially given a number of samples from NASA's Jet Propulsion Lab where they had graded between well-known alloys without sort of a design aspect. So the idea here was, okay, if you just blend well-known alloys, you're going to end up with cracking and failure due to the fact that you have intermetallics present. So our goal then was to say, well, how do we make sure that we can get from one composition to another composition without failure? So the initial approach that we came up with was this, I'll denote as a feasibility diagram for deleterious phases, where we said, okay, well, everything that we'd looked at in those previous samples showed that we could predict the phases if we looked at two extremes. So equilibrium and then Scheil solidification. So what we're going to look at here is we're going to look at a ternary element space where we could say that a composition is feasible if we have under a certain amount of intermetallic phase. That's a user-defined value, and here we'll take that to be 10 atomic percent. If we take a look at equilibrium, which is relevant, or if we think about heat treatments after processing, or even some of the repeated thermal cycles that we see in additive manufacturing, we can then take a look at every composition and see if it's feasible or infeasible, meaning it has under or over 10% of intermetallic phases. And we do the same thing for Scheil. So Scheil is saying we have rapid solidification. What are our solidification products? And we stack those two together because those are our two extreme bounds. And we would say that we would only be interested in exploring this green space where we have a lack of intermetallics. And so to demonstrate this, we looked at this for grading a stainless steel to a Ti-6-4. So we take this simplified material system, and we can plot out all of the possible feasibility diagrams as shown here. So these are all of the diagrams, ternaries for that particular system. And there's actually only one way that we can put those together like a puzzle to get from stainless steel to Ti-6-4, and that's shown here. So this tells us we could go from stainless steel to nickel chrome to vanadium to titanium, and equilibrium and Scheil predict that we will transition from FCC to BCC. So we're avoiding then the intermetallic phase formation by introducing lots of intermediate steps. This was fabricated by Ames Lab. It wasn't optimized in terms of processing parameters, but what we were interested in was, do the phases actually transition as anticipated? Meaning, do we go from FCC as equilibrium and Scheil predict to BCC as these both predict? And we saw that we very well followed the Scheil predictions. However, so this was good in terms of avoiding intermetallic phases, but we did still have cracking when the chrome was introduced, so up in this corner here. So we also now have integrated welding, crack solidification, crack susceptibility criteria, where each of these would say, each of these 5 criteria are different methods to say whether or not you expect a crack during solidification. And each of these are in different scales, but if we normalize these and plot these, we can see that each of these has a hot spot where chrome is introduced. So that would be represented by a dark region in our crack susceptibility. So we can now merge these two techniques together and say, okay, we have now a map that would tell us where to avoid compositions based on intermetallic phases. Those are the colors. And then the grayscale on top of that would tell us regions to avoid if we want to avoid solidification, cracking, or things that we would need to modify our processing parameters. So we've used that to successfully grade stainless steel to Monel. If you try to grade stainless steel, if you try to merge these two directly, you'll get cracking due to copper segregation. But if we add in some nickel to avoid sort of the crack susceptibility region, we're able to successfully grade between those two components. And one final thing I want to comment on is then, okay, if we think about these paths, we have some tools now to decide whether something's feasible or infeasible or assign different penalties for different compositions. We can also now think of this in terms of what tools can we use to get from one point to another point. So in 2D or 3D, we're representing the compositions as nodes and then their connections as to how we can get from one to the other. And so this is a tool that was developed by a former graduate student, Adam Petruski, where if we take a look and we've merged now that path planning with our feasibility diagrams, we have the feasible space in green and red is infeasible. And we can start to think about how do I get from one composition to another, either with a shortest path, or we can stretch space to minimize the selected gradient. And if we assign properties now to these different nodes, we can now say that we want a smoothest property or a path maximizing a selected property or so forth. So there's lots of different things that we can now integrate into this approach, which generally allows us to go from one composition to another. So in summary, then this one is we've designed a compositional framework that allows us to get to compositional pathways for functionally graded materials to avoid cracking due to phases as well as crack susceptibility. And then this provides us tools for spatially tailoring properties, but it also gives us a path for designing new alloys amenable to AM. So the three parts here are sort of summarized here. The first one is thinking about certification of additively manufactured parts with harnessing in situ process data. The second one is thinking about how we can think about stress state and defects and define critical defects to avoid so that we can use a part in service. And then the last one's looking at functionally graded materials. So that's all for today. Thank you.
All right, very comprehensive talk covering the material science and the methodology and the mechanics. Give me a second. We are going to have about 10-minute break because we are already ahead of schedule. So the presentation will resume at the 15:40. 10분 동안 이미 스케줄을 많이 조금 앞당겨져가지고 빨리 발표를 해주셔가지고 정확하게 10분 후에 3시 40분에 다시 발표 시작하도록 하겠습니다. Audiences have a chance to say hello each other to the international speakers this time. All right, next will be given by the Professor Wataja from the University of Birmingham. The talk title is 3D Printing from the Laboratory to the Industry. Please welcome Professor Wataja.
Thanks very much for the kind invitation and today. So I thought today to put some slides summarizing some of the work I've been doing at the University of Birmingham and in particular what managed to go to the industry and what failed to go to the industry from the time I've been here at Birmingham for 15 years. We run a large research group in Birmingham. There's about 4 or 5 academics working on metal additive manufacturing alone, with myself as one of them. We have also a good number of facilities on additive manufacturing. So for instance, we have a number of Renishaw machines, SLM solutions. More recently, we got an electron beam machine that's just been delivered today, actually, and a green laser machine. Some of them are quite unique. So the SLM solutions machine has 4 lasers, which can speed up and quadruple the speed of deposition, giving us a chance to generate larger components in a shorter time, as well as a DLD platform, which is the top one there. So this is the ability to deposit material quite rapidly, putting around 2 kilograms of titanium per hour of titanium, for instance. Over and above binder jetting and hybrid additive subtractive systems, plus hipping for post-processing and other techniques. So one of the things we do at Birmingham is that most of our work is actually inspired by the industry. So we started working on the aerospace sector, working with the likes of Rolls-Royce or Collins Aerospace on aerospace components like jet engine components or heat exchangers. And from there, we moved into work with the space sector with generous funding from the European Space Agency, doing space hardware, for instance, or thruster components or radio frequency devices. And then we moved into the medical sector with more work on medical implants and stents manufacturing. And sometimes even we went into some unusual sectors like quantum sensors, which I'll talk about today as one of the fields we worked on. Other sectors include motor racing. Again, this is a great sector to work on with additive manufacturing because you don't need too many components. And then presently we're doing a lot with nuclear fusion, essentially the idea of trying to create a small sun on Earth. That's the aim. But if we can find the right materials that can contain that sun on Earth.
Then we venture into some other exciting topics like 4D printing, so relying on materials which are super elastic in their performance or that can deliver temperature dependent or magnetic field dependent performance as well. And then last but not least is some work on application of auxetic materials in shock absorptions or so. To get into the topic straight away, the first question I asked today is additive manufacturing struggling to deliver? And I'm surprised that until now I have not seen this curve being shown, but basically the idea is as follows. Around a year ago, 3dprint.com website published an article saying RIP 3D printing, 1987, 2023, complexity is expensive. And what they were trying to pitch in a very pessimistic article, as I see it, that the field is struggling, that many companies are not growing at the same pace as we were expecting them to be. But they did mention some points which did make sense when they were mentioned. The first challenge that they listed was that the research funding for additive manufacturing is facing some challenge. The point that it's competing at present with some other topics like energy, for instance, as well as AI as another topic. In a way, the money available is finite at the end of the day, so we looked into other topics to prioritize the funding into them. The second point was that the market remains to be dominated by a few large companies when it comes to the service provision or when it comes to even the machine the development. If you compare that, for instance, to the CNC manufacturing sector, which has a lot of manufacturers in it. The third point is that service providers are small. We don't have enough of them. We need more. They're not widespread as casting foundries, not widespread as CNC workshops, as I mentioned. And so there is a need for more of them to be available to get the topic, to get the field to grow even further. And there are some sectors like the aerospace and biomedical sectors, surprisingly, are still in post-pandemic recovery. So although we may be like 3 or 4 years after the pandemic, we still see some of the impact that the pandemic had on these sectors until now. Finally, that there are some challenges in the field of additive manufacturing remain unresolved, like the feedstock cost, like the equipment cost, and so on. And as a result, they concluded that additive manufacturing is yet to deliver. So that's the how some people in the field, in a very pessimistic view, may see additive manufacturing as being in. But at the end of the day, the struggle to deliver is very common in a way, or the struggle to deliver from the industry, from the lab to the industry, is also very common. You're all familiar probably with the concept of TRLs and how that at the universities we're trying to operate on the level from 1 to 3, and the industry is looking for implementation from 7 to 9. But then between them, there is the valley of death, where you struggle to move things from the universities to the industry. And this is potentially where additive manufacturing may have struggled with some of the ideas that people have been proposing in the literature or from their studies, to be able to move it from the lab into a common technology that's being used in different sectors. So in my talk today, I'll be talking about basically some case studies that I was involved in. Some of them failed or succeeded in making the transition from the lab to the industry. So I'll be specific about 3 case studies. The first one is additive manufacturing of nickel titanium shaped memory alloys, or nitinol as people may call it. The second one is additive manufacturing of quantum sensor components. And the third one is additive manufacturing of tungsten. So let's start with the first one. So things that didn't work out, which is nickel titanium shaped memory alloys. In 2017, I got funded on a program to 3D print nickel titanium for stents. The idea came to us from cardiologists who were saying, essentially, as we all get old, our arteries start to have these stenosis sites from old unhealthy food and lifestyle that we have been enduring throughout our lives. And as a result, you may need to put or fit 1, 2, 3, 4 stents in one patient. And because of that, it ends up being a very tedious process for a cardiologist to put all of these stents. So the idea was, why don't we try to design a stent that takes the anatomical description of the patient straight away, customized for the patient to do the job. So we spent some time 3D printing the stents, and the development we found at the end, yes, we can print some stents. They look, as you can see, nice and flexible. They are as similar to what you might get from a commercial stent. Stents are used in not just in cardiac stents, they can be used in the esophagus, they can be used in the lungs, so they have a lot of applications that can get them to be used. To get from the concept to the application, we have obviously seen some technical challenges. The first technical challenge was the surface finish, the quality of the part we're trying to make. So if you look into the as printed stent, this is how it looks like. so the top there, so that's as printed stent. And then it had to go through a long process of surface finishing and electropolishing to get into the nice, shiny looking stent surface. And if you see this under the SEM, you'll find how an as-built stent looks like. It's around 0.5 mil, this scale bar. But then after etching, it reached to the right geometry of around 80 microns, which is what you want for a nice bendable, flexible stent. The other key problem that we had was that if you try to print nitinol, which is meant to be 50-50 nickel titanium, you end up getting some nickel evaporation. Nickel will selectively evaporate. So we worked with our colleagues at Oxford Universities back then to simulate the effect of the process parameters on the evaporation. So you know roughly what sort of scan speed and laser power will generate how much nickel evaporation. And we simulated that by computational fluid dynamics. And as an outcome for that, obviously we know how much nickel is being lost, and we can add more into the alloy at start. So instead of printing a 50-50 nickel titanium, we print a 55 nickel, 45 titanium, so that we can account for the loss that happens in the nickel during the process. That all worked, and we proposed the idea. And then interestingly, during the project, Johnson Matty, who was one of the partners, came to us and he said, we probably have a better idea for you than just printing the stents. One of the problems in making stents is that it's a very long process. So to make a medical stent nowadays, you initially start by having an ingot, and then you extrude it into a rod, then you drill a hole, then you draw it, and then eventually you laser micro machine it to make a stent, whereby you have lost 95% of the material you started with. And their idea was, why don't we just simply print for us tubes? Forget about printing stents. Print for us the raw material of the stent manufacturing process. So in addition, if we avoid all of these processes of casting, thermomechanical treatment, drawing, and straight away make the tubes. And we liked the idea, so we said, fine, we're going to try it. So we filed a patent for it in 2011, and we've done the proof of concept of the idea. So essentially, we looked into making a tube from nitinol. We get the tubes, we get them laser micro machined. This is how a stent looks like. You can obviously make a variable diameter tube. You don't have to make a perfect tube. You can make a customized to the shape of the arteries that you're trying to open up. And eventually you get the stent made. It can be used as a commercial stent. The outcome was quite good. Shapes were quite nice. You can get into the right shapes. We have done the qualification for the stents based on the STM standards, obviously. So looking into the bending of the stents by simulation and by testing and so on. But still, that failed to leave the lab. So we initially thought that we can make this technology and we can commercialize it as being something which is custom medical device. So essentially you can apply for a waiver or an exemption to manufacture it. But we've still realized that we still have to go through a very tedious medical qualification process, even though it's meant to be a custom device. In the UK, at least, you have to go through ex vivo trials, animal trials, clinical trials, in-patient trials before you get into full commercialization. And for many people, that was always a problem when you talk to them, that we know what we're doing, why change? Current stents do the job, so why do you want us to look into something else? And also with the medical industry also being to some extent being risk averse, they find the change quite costly. So it turned out as at the start when we started the idea, when we asked basically who wants a 3D printed stent, everybody said who's willing to try them out. Nobody's trying them out. And this is what happened essentially with the story of the stent. So until now, we discontinued the patent, of course, when we found there is no interest. But in a way, the technology has been fully reached to the maturity level, but yet to be tested in the industry at some point. Now there are things in transition, which is additive manufacturing for quantum sensors. So maybe some of you do not know about quantum sensors, but this is a sensor that can be used to detect gravity fluctuations. So this is some work with the School of Physics who have developed these sensors. The sensors rely on a technology called the atom cloud, where you use lasers to cool down the material to a very low temperature. And then after that, the condition of the material inside becomes very sensitive to gravity changes. So if you put them on a satellite, they will know if there is tungsten in Chile, if there is oil field in Canada. So they can detect the local gravity fluctuations from one place to the other. Of course, if you're going to put this on a satellite, it needs to be light. So it needs to be a light component. And this is where additive manufacturing can be quite handy. That's how a quantum sensor looks like when you put it inside a package, but the package from inside even is full of components like this with a lot of features inside. And with this being a gravity sensor, it needs to be very, very protected from any interaction from any magnetic fields around it. And as a result, we started to use a material known as a soft magnet that will pull out all the magnetic field lines into it instead of actually allowing it to interfere with what's happening inside the sensor. So from a printing point of view, yes, you can print the material. We've spent some time qualifying it. We've obviously designed structures that are multi-walled, for instance. Printing was pretty fine. It's a nickel iron alloy, so it's not too complicated to try to print it. And eventually we've done some tricks in the process to get it to work. So we needed to do some tweaks in the crystallographic orientation of the material by printing it at a certain angle to allow us to get the maximum performance. And then as a result, the parts we printed, when we talk about their shielding efficacy, if we compare it to the standard material, we are way above the standard material. We're getting very high shielding capability from the material, even more than the target. Of course, with some heat treatment, with some hipping to get into that right performance. But in a way, that reached to the point that we are actually happy to, deliver. It's basically no qualification required beyond the ability to deliver the magnetic performance, which it can deliver. It's a niche application. It's a $7 billion industry because shielding is used in many sensitive components, in satellites, even on aeroplanes to protect them from any electromagnetic interference. And we have even expanded that now to other components. So many of the magnetic shields we print are used in medical imaging devices like magnetic MRI devices, into vacuum components as well as other materials for that application. Now this is in transition for the industry. So the Magnetic Shields is a company in the UK that works in this field, and they're now starting to use this technology and allow the spread of the application forward as well. Let's look into things that can sometimes work, which is additive manufacturing of tungsten. Potentially since 2014, I've been working on putting tungsten into nuclear fusion through a number of programs with the UK Atomic Energy Authority. And the idea is that, as I mentioned, nuclear fusion is all like making a small sun on Earth. The temperature is quite high. It's like 150 million degrees Celsius somewhere in the plasma. So in that part in the plasma here. And these walls are typically made out of tungsten or vanadium or some steels. And we need to find a material that can be used to be able to protect from the interaction with the plasma around it. The only material of choice is limited. So it's tungsten, as I mentioned. And the reason for that is if you talk to people who do nuclear fusion, the first thing they show to you is the periodic table. And they tell you, we don't want that, we don't want that, we don't want that. And then eventually you go to the point, we can happy to live with tungsten or tantalum and chromium and vanadium and very limited number of elements in the entire periodic table, mainly because of the activation of these materials. You don't want to use something which is going to be active for over like 1,000 years or something like that. So you're happy to work with tungsten and tantalum, but as you can see, plenty are in red, including things like oxygen, for instance, which will form at some point. And this is potentially one reason why fusion remains 30 years away. Every now and then you have to find the material to deliver the required performance. So when we tried to print it, of course, tungsten with laser powder bed fusion is highly susceptible for cracking. It will suck a lot of oxygen, so it always cracks. Even with the best practices, you're going to get some tiny little cracks into it, however hard we tried. But around the same time when we were doing the work for fusion, a company in Manchester came to me and they said, Motaz, can you print this shape for us? So this is an X-ray collimator. It's a device that gets X-rays to move in one direction. It's basically sits there doing nothing, doesn't take any loads, doesn't take any other factors. And we said, yeah, let's give it a shot. We tried it, we printed it, and we tested it actually, and it did shield up to 88% of what solid tungsten would do, which was for them was quite good. Knowing that the only other alternative process is to laser machine it, to machine it. And every time you get the hole wrong, you scrap the entire part. So it was not a bad idea to try to make it by additive manufacturing. Eventually, it was commercialized. Now it's being sold in the market. And the university signed with the company a licensing agreement. In their first year of sales, they sold, I think, around worth £250,000 of sales. My royalty for that was 150 British pounds. So you can see sometimes academia doesn't pay well when it comes to licensing technology. But the key point is that, yes, it was cracked. There was some tiny little cracks, some micro cracks between the grains. But in a way, it does not compromise the performance. It does the job. if you're using this for collimation or for microfocus radiotherapy, it will do the job. More importantly for us as metallurgists, one thing that we provided to the company was that if you want to print tungsten, you have two options. You can buy a very expensive powder like that, which will cost you around maybe $200 a kilo. Or you can buy something which doesn't look very nice, like that one, which will cost you half the price almost, £100 a kilo. And if you're happy to live with something which has some cracks, you're happy to live with something which is not necessarily the strongest possible part, then in a way it will do the job and it will deliver on the performance. So eventually that was the thing that we can bring as well to the technology to make it more affordable and to do the job in an easier way. So to conclude, I think AM needs to adapt to the changes in research funding directions. You can see that there are some sectors that will grow, some will decline. Energy at the moment is growing. That's why we're doing more work now with energy and nuclear fusion and other programs. There are tools like AI that are coming into application. We need to basically use them and try to make use of their abilities. But also we need to commoditize, basically look into the technology and look into it as a product that needs to be sold in large numbers as well. One time somebody told me that the best product in the world is something that will sell a lot like a toaster. You want additive manufacturing to be used for toasters so that we can sell more machines and use it more commonly. What I found from my experience in working in this field for the past 15 years is that there are lots of opportunities, especially in non-structural materials. True, they are niche applications like quantum or like fusion or like stents, but still they can give us the chance to exploit some unique mechanical, thermal, and magnetic properties of the materials and deliver on them. But the main challenge is that these are very niche sectors. They are not wide enough. They are not a toaster. They are very limited to some extent in their potential impact. And this is where we need to find more of them so that we can justify what we're doing. And one last lesson I learned from working in this field that is multidisciplinary projects are a great opportunity in identifying new applications in AM. Working with cardiologists or physicists or people in nuclear fusion or X-ray collimation was quite helpful for me to engage with different sectors and to do more actually from the work we're doing. And finally, I have to thank those who paid the money over the past 14 years, of course, and thank those who have done the work. And thank you again for the invitation. Thank you.
All right, so that was a very comprehensive talk regarding what's going on in the University of Birmingham. All right, so this will be the last talk. That will be given by the Dr. Paul Witherell from National Institute of Standard and Technology. Dr. Witherell is the program manager with it, and then his talk title is Preparing Additive Manufacturing for Gen AI Solutions. Right. Please welcome Dr. Witherell.
All right, good afternoon, everybody. So this is a newer presentation for me, and it's sort of a new research interest of ours that we're starting to explore. So the thought process behind it is that I'm talking about, when I talk about Gen AI here, I'm using the Gen AI as more of a vague term just because people are getting familiar with the term, but I'll contextualize the choice of the Gen AI term later on in the presentation. But I wanted to talk a little bit about how some of these emerging artificial intelligence type algorithms could be utilized and may affect some of the research that we do in additive manufacturing. So I've been working in additive manufacturing for a little over 12 years now. My background is more in the information sciences crossed with mechanical engineering, working with ontologies, information modeling, and data modeling for the early part of my career. So here's a quick outline, sort of I'm trying to do a little bit of storytelling here. And so the goal here is to kind of give you a little idea of what this story looks like. So we're going to start a little bit with describing the additive as a digital manufacturing process and what the implications are with that. We'll talk a little bit about the data that we've generated and that utilizing because of the additive as a digital manufacturing process. I'll talk about the role that we've seen with these machine learning algorithms in the past few years, and talk about the emergence of some of the more general artificial intelligence, generative artificial intelligence foundation models, LLMs. And then talk a little bit about, how might some of these things come into purview in the future? How might we be able to utilize them? What are the steps that we need to take as a community to better utilize them? So additive manufacturing is a digital manufacturing process. So, this is nothing that I think all of us know in here. It's become a proven production means. So we've heard a little bit about that through earlier talks today. Folks are being able to create additive manufacturing parts, to give a design, create a part. It's not necessarily push to print though, right? And so there's a lot of back work that goes into creating these parts. There's a lot of getting the parameter settings right, getting the machine settings right, getting materials just right to work with the design, and then fabrication of a part that then has to be tested many times before we can send it out to the fleet or send it out to be utilized. So it is a proven production process at this point, but there's a lot of opportunities to mess things up and get things wrong. And so, what we're looking at this slide here is some of the information that goes in this design to product transformation across the value chain of an AM part. What we have seen, you can make the argument that this has been a large contributor to what we've seen for the additive manufacturing becoming a production process, the maturation of additive manufacturing as a production process over the past, 15 years to 10 years to 5 years. And we can see how it's drastically changed. Our machines that are 10 years old are very antiquated at this point. Our machines that are 5 years old are getting antiquated. And what's driven a lot of that technology development? A lot of it is driven by our ability to observe what's going on in the process, the ability to censor these machines, and the ability to be able to learn from what we're seeing in the process. And so, not only the sensors, I guess I'll start here, but we're seeing all this different types of data that's being generated across the additive manufacturing value chain, from the design phase to the planning phase to the fabrication phase, all the way to the inspection phase. And so we're using lots of different sensors, lots of different tools, lots of different mechanisms for measuring our additive manufacturing parts and our processes. And we're creating lots of data. And, one of these early challenges that people have talked about is we don't have enough data. Then we realize we have lots of data and it's all segregated. It's not handled the right way, not stored the right way, not curated the right way, not labeled the right way. And so that's where we've seen this emergence of machine learning. And I think the argument can be made that a lot of the concepts that are deployed in machine learning are concepts that have been adopted for many years prior to, and they just recently came under the umbrella of machine learning. And we can make the same argument for digital twins now. Of course, artificial intelligence has been around for 50 years, even though, what it looks like continues changes over the years. But this is, interesting. We did a review of machine learning back in 2019. So I just took a snapshot from that paper. And it was in the middle of 2019, so there were a couple of papers there. But if you looked at machine learning and additive manufacturing, that's really what the results were just 6 years ago now, and it's really ubiquitous in what we do now. And so it's looking at how much the environment has changed over the past 5 years, and what machine learning has done. I think all of us probably practiced it, used it, been exposed to it some way, shape, or form, and how we handle additive manufacturing data. So here in the figure, you see a little bit of, what are some of the opportunities for deploying additive manufacturing or machine learning additive manufacturing early on with the planning for the design, the monitoring, parameter selection, and into the qualification side of things. So here, success. So we can, I think, ideally, all the folks here that have been involved in additive manufacturing for some period of time now have successfully leveraged machine learning in some way, shape, or form in their development of a part, process, material, somewhere along this value chain. Here's an example on the left here of how we've leveraged machine learning at NIST to develop a control algorithm for real-time control that demonstrate real-time control in the laser powder bed fusion process. The idea starting with regression modeling, be able to anticipate this is what the melt pool looks like. This is what the melt pool should look like. Using machine learning techniques to anticipate what the control parameters should look like to generate the melt pool that you want. And so, we've been able to see this across the additive manufacturing value chain, from materials development to generative design, process parameter selection, a lot with melt pool monitoring, control, looking at the different, looking at the data and being able to clean the data and label the data. Machine learning is becoming more and more important there. And of course, the part inspection, looking for defects and defect detection. And finally, starting to look at those correlations. We're starting to throw terabytes of data. Nobody's going through these terabytes of data manually. So more and more folks are looking to leverage the machine learning in order to utilize and take advantage of the data being generated. And so some of the challenges, that I just talked about, I think, is where we're hitting some roadblocks in how we deployed machine learning. The idea of, there's lots of standard practice for handling data sets. And so folks are generating the data, utilizing the data, but they're developing their solutions to fit their data sets and their data needs, not necessarily developing solutions for these ubiquitous data sets. There's an absence of common data structure. So a lot of times when you look at what sensor you're using, who manufactured that sensor, that's going to determine how your data is created and stored. Lack of tools for organizing the data in an easily accessible manner. A lot of times, the very prevalent term that we've used in the past, that, data is siloed, right? So you have this data that's being generated off of the machines, or off of the part, off the organization, and it's accessible when it needs to be, but it's not accessible when somebody looks for it, but not always accessible when it needs to be. And of course, it's challenging to transfer learning between data sets. Even within an organization, you finish some parts, create some parts, generate some data for one material, one design. We all know that doesn't necessarily work for the next material, the next design. And the way that we use our machine learning right now, that means we have to recalibrate our models, retrain our models, redevelop our models to meet with the new application in order to take really advantage of some of these algorithms that we've developed. So this is where I want to talk a little about the recent emergence that we've heard, and I think we're all mostly familiar with, ChatGPT, GPT 3.5, 4.0. The reason, again, why I titled this talk Generative AI, or Gen AI, because I think that's what the concept that most people are familiar with, but it's part of a more broader concept of foundation models, which I myself am still getting familiarized with. But the idea that there's some basic models that can be retrained to serve different purposes. And so there's a lot of different ways that you can show these models and kind of present what these relationships look like. I found this picture, and I have it referenced in a different version of this picture later on, out of a web post from some folks at Intel. And here they talked about the large language models, LLMs, in the generative AI. And you see a little bit of Venn diagram where LLMs can absolutely be used for generative AI, but not LLMs all have to be generative AI. Generative AI can absolutely mean LLMs, but not all LLMs are generative AI. And then you see these foundation models, this idea that you can develop these machine learning models that we retrain to meet specific needs. When we're seeing this is all part of that deep learning concept, the idea that all this can fit into this machine learning paradigm, about looking at how the information is utilized and what we learn from the data that we gather. And one of the things that I want to take away from this figure, and why I like this figure so much, is that with those little blue boxes in the middle labeled A and I. And when I see that, when I associate with it, A and I stands for is artificial narrow intelligence. And I like to think of how we adopt machine learning now really fits in that A and I paradigm. The idea that we have very specific data sets to create very specific solutions for very specific problems, but we don't have that greater breadth to handle the diversity of data that we need to. So we have these great new Gen AI solutions, and we can use them. We want to use them. What happens when we use them? And so obviously we're seeing rapid reduction here in the last 2 years ago. The select few used ChatGPT. A year ago, everybody was talking about ChatGPT. Now it's probably already hyped out a little bit and looking down. But again, that LLMs is just one part of the larger foundation model, which is absolutely still growing as an area of opportunity. And so the question is, as these tools mature, what does that mean for our community, for the folks that want to be able to leverage them out of manufacturing? We're seeing that a range of data can be processed. We're playing with something right now. We're trying to recreate some of the some of the regression modeling that we've done with melt pools, if we can use some sort of generative AI tools. And one of the challenges is the specialized tools to take images as an input and do images as an output that still fall under this foundation model umbrella. And so there's different variations and there's different combinations of some of these foundation model tools that can be used to solve these different data sets. But they're, each one has a certain solution, and they're still emerging as far as what their core foundation, I guess, attributes are. The performance is inconsistent. What happens is when you query it, when you ask it a question, if you will, if you're looking at a GPT, you're looking for an answer and it will return an answer, and then you can ask it something very similar and it will return a different answer. And so we know it, I'm sure more and more students are using it. We know it's using Grammarly. I know professors are looking at it for, if they're writing entire conference papers out of these things. So we know it can do some pretty amazing things. So why can't it solve some of our problems the way that we need it to? And so, one of the, I'll talk a little bit about, how we can overcome some of those challenges. But right now in the bottom right there, you see, PV maps, power velocity. And you just say, hey, can you give me a PV map for this material? And one of them gives it a straight line, which is not right. And another one gives it this really creative looking diagram or something. They're both nonsensical. But again, we know these tools can do something, but how do we get them to do what we want them to do? In the bottom here, you see the melt pool. Say, can you give me the melt pool, what the melt pool is going to look like when I use, 400 watt laser on an Inconel alloy? And, this thing looks like some sort of volcano erupting in outer space. And so again, you're seeing something, you want to tease something out of it, but it's not giving what you want to do. So we have these new tools that are available to us, but they're not responding the way we want them to. So what can we do from our community to try to address that? The first and easy answer is, we don't develop artificial intelligence. So we can inform ourselves and educate ourselves on the different tool sets, the different capabilities of the different tool sets, understand the idea of the architectures, the modalities of how they handle the data, how they use the data, what are some of the common tools, and what are their capabilities. And then we can ask the folks in computer sciences to say, this is great, but it's not good enough. You need to make it better. But the question is, that raises the challenge of, okay, what does that mean to make it better? This is a tool that's already can write an entire story. It can write your emails for you. It can create these amazing pictures out of images. So how is it not good enough for us? We can already do all these amazing things. And so the question is, what can we do in additive manufacturing? We know there's powerful tools. How do we adopt them in the additive manufacturing? Characterize the generative AI and foundation model tools to gain insight of potential applications. Better understand how the abilities, the capabilities of the tools correlate with our needs in the additive manufacturing community. Identify and develop metrics to evaluate the application of Gen AI and FM tools in AM. And this is something that we're working on really right now, and it's neat because it gives you these nonsensical answers. They're wrong, but how do you evaluate them objectively that you can tell it how to make it better, or you can train it to make it better, you can prompt it to make it better, because it gives such a diverse set of responses, a lot of different ways that can be done. And so what do these metrics look like that you can start to evaluate and train on? Develop best practices for retrieving consistent results in model applications. So this one kind of goes hand in hand, this idea of prompt engineering. And when you want to train a model, you want the model to give you consistent results. But the problem is if you ask the model and you tweak how you ask the model, or how you deliver the query or the prompt to the model in different ways, you'll get substantially different answers. And so before you can even worry about improving the model, you have to figure out how you're going to be consistently querying the model to try to get consistent results before you can worry about getting the metrics and the training it. Develop best practices for model selections and best practices for adopting and training. So this is some early work that we've done in the area looking at benchmarking. And it's been interesting work. This is something that we just published this last month. We presented at a conference with the idea of, in the most generic sense, what are its capabilities? Can it create an image? Can it create a chart? Can it create a graph? Can it read math, right? These are basic agnostic capabilities that maybe you want to know about the capabilities of this foundation model. And so we can get some basic metrics out of there, but then we want to go into the domain metrics. And so here, if we want to start to look at developing different metrics for different requirements. So the design domain traditionally been more focused on design requirements and maybe also how well you can handle images, figures, designs, and models, and interpolate, extrapolate, and generate new models. In the process planning, a lot more parameter handling, build and monitoring. There's a little bit of a concern, particularly in the control, the idea of how fast can this send it back if we want to use something in real-time control. In the testing, we work a lot with the 3D space and also looking at different modalities of information and data. And so the metrics for those different domains, what are the metrics that we want to develop? What do we want to evaluate this tool? What does it mean to do good? And so there's a part that goes into starting to develop the metrics to help assess what is good. And then finally, in the problem solving aspect of things, okay, my melt pool shape has to have, a circular shape or an oval shape, and it has to have some sort of tail, right? Okay, maybe it does great. Maybe I can get something that gives me a circular shape and a tail, and I say, this could generate a melt pool. But then if it's completely off on what it is that you want to do, you wanted a melt pool that was supposed to be like, 100 microns, and you end up with something that's, 10 magnitudes off. So obviously it kind of got the gist of it, but it gave you something way off in different space. And so it's interesting kind of working through these problems as far as how do you get it to tease out what you want to tease out of it. And a big part of that is the metrics. As I mentioned, another part of it is a prompt engineering, and the idea of how do you query these models in a way that that you're querying it consistently, because if you query it differently, then it's possible to evaluate how well it is trained or how well the results are, because the results are being contaminated by how you query it in the first place. And so there's a big part of that prompt engineering aspect that's still kind of being teased out. And again, this goes back to the additive manufacturing. What are we using these models for? What do we expect these results to do? What do we want to reuse them for? How can we simplify some of these transfer learning challenges and make these robust models that might be applicable in different areas? And so a big part of that, we also just did a paper on this in the prompt engineering, is studying that and looking at how much the changes of the information, how much the results change just based on how you query the models. And finally, before we can even get to training the models, we really need to understand what their capabilities are and what type of variances we're introducing when we query it differently. But once we get those things done, then we can start looking at, okay, we know it does powerful model. We know it can do some neat things. How do we train it to do what we need it to do, what we want it to do? How do we leverage ontologies, physics-informed neural networks, the different specialized training data? Maybe we're looking at right now some agent-based solutions for linking up with ANIs for solving specific problems, domain-specific prompting. And so this is an area that we're just trying to scratch the surface on now. But investigating this in general, are there a lot of opportunities here? We all know, when we want to solve some of these more challenging, when we see what artificial intelligence is going to be in the future, we know that we expect it to be able to solve these broad, complex problems. And so how do we start preparing for what our capabilities are now? And to what extent can we really leverage these tools to help what we do in additive manufacturing? So looking ahead, Gen AI and foundation models potentially expand how we leverage data and AI in additive manufacturing. We need new metrics to explore an evaluation of application spaces. We need more consistent prompt engineering approaches to make sure that we're querying the tools in a meaningful way. Domain-specific models, when we want to get to the training, how do we start to constrain our solution space in a manner that we're retrieving solutions that we expect to see, and that makes sense. Agent-based systems have a lot of potential, and the idea that these Gen AIs are powerful enough that they can link up and use a system-of-system type approach or system approach in some of this problem solving. And we're teasing around the idea of the additive manufacturing test artifact. But what does a quote-unquote test artifact look like for some of these AI models where, giving a set of queries, giving a set of prompts, giving a set of information, how do we know how well our model is going to respond to our specific needs and if our model is good enough to solve the problems that we want it to solve? So yeah, this is again some work that we're just kind of starting, and I thought it'd be fun to talk about it today. Here are some of the references I use in creating the presentation. Thank you for your time.
All right, so thank you for our speakers for our valuable talks. It's time to panel discussion. So we need to prepare for chairs to be displayed, and as all speakers, please come forward to the stage.
Suggest to us for researching, especially for DD process. So we need to develop a new machine for DD for monitoring controls. So we researched a lot on the type of laser, whether continuous wave or pulse or QCW. So if you have any experience, I would be appreciate if you can give me the advice. Thanks for the question. Well, you have a lot of options. Depending actually what you want to process at the end. So most DD machines will be using infrared lasers. But then more recently we start to see papers coming out on systems employing green lasers. But even more recently blue lasers as well. So blue lasers and green lasers are quite helpful if you want to process materials like copper or any other reflective materials in general, because their absorptivity is better. Pulse laser is another interesting area to look into. There's also a result of interesting papers that talk about how we can control residual stresses through the application of pulse lasers. You can also control the microstructure, because as you pulse between on and off, you're generating advanced grade structures rather than columnar grade structures. It depends, let's say, if you start from the point of which material you want to choose, that can guide you on the type of laser you want to use, and then what you want to do with it. If you're making samples or components or small samples, let's say, of stainless steel or nickel superalloys, then having the ability to pulse can be quite handy to have as well. Yeah, actually, we are going with just a normal material like stainless steel 6L or titanium. And as this is for research, we will make small pieces of the AM products. But I hear the pulse type is not easy to control, but it's really good for controlling the heat and stresses on the product. So that is the reason we cannot decide on the CW or pulse type. As you know, there are many papers, they use the laser in CW mode and very rare in pulse mode. So that's why I asked that this question. I can add to that. So on pulsing, if you're trying to control the microstructure and control residual stresses, you don't need to pulse more than a few tens of hertz. So 100 hertz, 200 hertz will probably be more than enough for you. Because as you pulse at a very high frequency, you actually do not get any benefit from pulsing, because it's almost like a continuous heat flow. You're not going to have enough time for the heat to dissipate. So 100 hertz is
probably enough to get you working with stainless steel or other materials.
Anyone else can add additional comments regarding?
Are you going to build your own system? Are you going to build your own laser system? Okay. If you, I had an experience with building a custom laser powder bed fusion system. It's quite interesting because for research purposes, it's not for production, right? It's very important that you need to consider what's the size of your building volume. My suggestion is do not go for very large size. You want the capability of building your small samples for characterization with very little amount of so-called custom powders. Because if you just go ahead and purchase powders for your 3D printer, that's basically commercial available powders. It's meaningless for a researcher. Sorry, I'm not saying that. For research purpose, you want the capability of develop your own powders. Most likely you get a very small quantity. When you build up your 3D printer, make sure you go for smaller building volume. Even just 10 grams of powders will be adequate for you to come up with a good size sample. So that's the interesting point. Don't just be too ambitious. Say, I'm going to build the world's largest 3D printer. Don't go for that route. go for the world's smallest 3D printer, enable you to build up the samples adequate for materials research. For material research, you need a tiny amount. You don't need such a huge quantity. So the key point is track. You need good control on the software side, right? You mentioned pulse or continuous laser. The pulse laser, of course, give you the advantage of several times higher of energy density. I think that's the one. If you ask me, I'll probably go for the pulse laser design. But still, my thinking is you need thinking of a software as well. You need to have the capability to control your laser down to the molten track stage. You want to have the software to control planning. How are you going to scan the laser? So you know laser interact with the powder bed, right? You need to have the capability control all the way down to the laser track. Each scan, you have to know what is speed, at what moment you decide to make a turn, because the laser cannot continuously run at a constant speed. When you make a turn, the laser power will change, right? Because the velocity will change. So consider all those, get good control of the software and know detailed scanning strategy will enable you to link the scanning strategy with the resulting microstructure. Hopefully, you also obtain the detailed mechanical properties. It's a length scale issue. Build the small parts, you can go for the small scale mechanical testing. That's what I want to get, because you want to get the mechanical properties down to your laser track length scale, maybe 50 microns or even smaller. I think 400 watts is more than enough.
More than enough.
Yeah, I built once 200 watts. I guess you go for 400 watts with pulse. That's more than enough.
Thank you.
So do you have any other question from the audience?
Good afternoon, speaker. My name is Xiao Tong. I'm a student in Busan University. I have a question, I think, specifically for Mr. Brent. As you in your slide from first page to another page following, you state that the growth of the additive manufacturing for the last 20 years is quite considerably well. But either, I mean, as a whole, either machine selling or products. But I would like to focus more on the metal 3D printing. As you know, that in metal 3D printings is normally they use only the powder in the certain range. For example, let's say 30 to 60 micron. And as you know that in the powder manufacturing process, like we are using, for example, is gas atomizing or plasma atomizing, it produces a very wide range of powder, either for less 30 micron or more 60 micron as a whole. It means that the powder that are not counted is, I can say that useless, because we can sell only like 30 to 60 micron powders. So we can say that the yield of producing of powder is very low. Let's say it's 40 to 50%. It means 50% is we cannot use it at all. So my question is, as a small company powder manufacturer, what do you think? I mean, I want your opinion for the next maybe 5 or 10 years, whether my company would be survive, or maybe we have to give up in this business, or we still have a chance, I mean, to expand our business. Because as I said, we cannot cope this cost. It's too much. I mean, too costly, because the yield is too low. It's only 40 to 50%. Yes. Thank you.
Yeah. So a couple thoughts. I mean, there are some people looking at different ways of atomizing, to try to get a better yield, tighter. So those are interesting. I haven't seen them really reducing the cost that much overall, because those are more expensive than the cheaper atomization. So I think if you want to be able to use more of that yield, you're dealing with some interesting problems here. That if you have too broad of a particle size distribution, then, well, if you have it too large, then you have a hard time doing maybe the smaller layer thicknesses that people are wanting, getting the surface roughness that they're wanting. If you go too small, you have too much interparticle friction, or you turn up your gas flow a little bit higher, and it picks up the small particles and sends them off. I was involved with some ideas for some maybe new machines where we thought about and looked at, what should we be able to use really cheap powder? And you look at the cost of the powder recovery system, the powder spreading system. You'd have to maybe spread the powder and deliver it in a different manner. It'd be more likely to cause issues with the powder systems. So off the top of my head, I don't necessarily see a major shift coming right away to be able to use a much broader particle size distribution, because it just brings so many headaches into the system. I do see, though, on the larger particle size, maybe if you shift yours slightly to the larger size, I do see a lot of companies now looking at building really big parts with really thick layers. And so that's going to allow you to actually use you can't really put more fines in there, but maybe you can put more of the larger particle sizes in there and get away with maybe increasing the amount of your yield that you can use in the machine. So people are coming up, instead of, it used to be 20, 30, 40 micron particle size, 20, 30, 40 micron layer thicknesses. Now we're seeing a lot of people developing 60 micron, 90 micron, even 120 micron layer thicknesses. So now you can get quite a bit bigger particle sizes in there and still not really mess up the process. So maybe that'll help you a little bit with your yield issue, but those are just some of my thoughts. I feel your pain. I don't know how.
Yeah, actually,
I don't have a good solution for it,
if we see the chart, the growth is very well, but actually in the grassroots, like us, like small company which is producing powder, actually is very challenging to cope this cost, because as you know, the yield is too low. So I don't know, in the 1-2 years, maybe we have to close this business at all, or we have to do, because we cannot expand our business in this line. That's why what I want to say actually. But anyway, thank you very much for your opinion.
Do we have any other additional comment?
So obviously powder making has been there before additive manufacturing. And what people used to do in the past, and they still do until now, is that for certain alloys, you can reach to almost full utilization. So the very fine powders goes to metal injection molding market. And then the coarser one goes to powder bed. And then the coarser one goes to DAD. And even if you have coarser, you can go to powder metallurgy, like net shape hipping, for instance. So, but that only depends on the material you want to use. So if it's 316L, you will find people wanting the very fine powder. You'll find people wanting the medium range and the large size. But if you're trying to make a material like, let's say, tungsten, for instance, you'll find people wanting only a certain size range or a certain superalloy. This is where the challenge can be. So if your business is based on one of the alloys that are widely used across the board of techniques, then you'll achieve 100% utilization, and you'll probably sell it for 3 times the price that you're making. You're going to make a big profit. But if it's one of these alloys which are only specific powder bed, like aluminum, silicon, tin, magnesium, for instance, then the challenge will be what will you do with the fine and the coarse? That's the problem.
Yeah. Thank you very much for your comment. The second question, is it okay? Still have time? Yeah. The second question, directly to Mr. Muatach. Sorry if I'm wrong to say your name. Yeah. You explain in your research, you make the stand using nitinol from tube, right? It's micro machining, and then the drawback is it's lost the 90 to 95% of the materials, right? And then I have opinion. Why don't we make by using wire, for example, wire, and then winding it to make it stand shape, and then heat treatment, and then finish. In tube also is micro machining, and then heat treatment, and then control the austenite temperature, and then to control the flexibility. In wire case, they just need winding to make a complicated shape, for example, and then heat treatment, and then, why tube is more popular than wire? I want your opinion.
Thank you for the question. So let me tell the whole story. So commercial stents, as I was showing, you start from a big ingot and you go down to a tube eventually, and then you laser micro machine to dissipate. You lose a lot out of that. But remember that some of the cardiac stents are only 2 millimeter in diameter. They're very small. And some other ones are like 8 millimeter, or some ones in the esophagus can be quite bigger than that. The wire-based approach you mentioned is actually being used. So if you're making a big stent used in the lungs or used in the esophagus, yes, or the rectum, they do use wire-based approach. The only problem with that is you lose the opportunity to customize it, because you're using it on a machine where you just wind it into the shape you want. So this is why we get into 3D printing. We said, well, we can probably print a stent which is customized to the shape of the artery. If the artery is big at one point, we make it big. If it's small at one other point, we make it smaller. So essentially, the cardiologist, when they fit a stent, they open a drawer and then they pick a 2.5 stent or 2.8 stent. What if the patient is 2.75 or 3.78? So this is where you want a custom stent to allow it to be fitting well. But the wire approach is being used already for bigger stents until now, but not customized.
Customizing is the key. Thank you.
All right. Do we have other question?
I have another question regarding Gen AI. We searched a lot about the machine learning methods used in other papers. We found that mostly supervision or unsupervision. But my question is, why reinforced learning is not suitable for in situ monitoring, especially in DD process? I think it is really applicable for optimizing process parameters with reinforced learning. So, do you have any experience or any advice?
I'm sorry, I have trouble hearing, but reinforcement learning. Reinforcement. So we've leveraged reinforcement learning for the in-process monitoring. Is that what you were asking?
Yes, in situ monitoring. For in situ monitoring and optimizing the process.
No, yeah, we've done that at NIST. We've leveraged. We have coaxial imaging on our laser, and so we've also built our own machine. I'm sorry, I had trouble hearing your question before. So we have a single laser 400 watt machine. We're upgrading to a dual laser, I think 500 watt each, coaxial imaging. And so what we have these milestones that we achieve, that we aim to achieve every year, our major milestones. And our major milestone 2 years ago was demonstrating real-time control in powder bed fusion. And so what we did was we leveraged the regression modeling with the prediction models that we gained. And so that was that one chart that I had shown next to what are the things that we can leverage for machine learning. And so we were able to demonstrate, building on the regression modeling, that we could demonstrate what the next expected melt pool shape was based on the previous melt pool shapes, and then adjust accordingly to get a more consistent melt pool size across the scan path, and be able to make those adjustments in real time prior to the melt pool moving, and being able to demonstrate that we're able to get more consistent builds. I think we were measuring discrepancies in height, if you would, during the strategy, and so we would get to more consistent layers when we were using our real-time control.
May I ask how many parameters could you optimize with your system? Because there are many parameters.
Which parameters were optimized? Definitely just power. I think it was just power and velocity that we were messing around with.
The most.
We have our in-house system, so we have the ability to completely control our scan strategy, so we can change direction. We're leveraging something we call time step digital command, and so we tell the machine where we want the laser to be at a certain time step, and where we want the laser to be at the next time step, and then we tell the machine what that shape should look like, and those things. So we actually have we've done our own in-house building control paradigm for controlling our system, that helps us do some of the process control that we've been able to demonstrate.
So, sorry, did you use edge devices to capture data or just PC?
Say that again?
For capturing data, did you use edge devices like the embedded systems or just PC is enough to take the data?
For sampling data to
signal. I mean the signal, or for image processing, you need to get data from the system, right? So
yeah, I mean, I guess we could call them edge devices for sure.
Okay.
So we the system that we set up was developed for monitoring and to add new monitoring equipment to the setup. So it was an in-house built cloud-embedded fusion system. We call it the additive manufacturing metrology test bed. And the goal of the system was to be able to implement different monitoring devices. And so it's very much set up not to do builds, but only to measure the process and to explore the process. And so we don't do a lot of edge computing per se in the sense that we need to move to the next build, because every run that we do is really just to experiment, to study the physics and the phenomena within the process.
Okay. And sorry, is there any public project for making a database for AM data through
So
the GenAI?
we have we developed at NIST one of the first publicly available metals additive manufacturing database. We call it the AMMD. So it was at ammd.nist.gov, and the goal behind that database was to make data available to public consumption on laser powder fusion process. Another goal of that was to give a schema template where folks can look at what are the process parameters, what are the material properties that should be looked at and stored, how they should be curated. That database is a little bit, is down right now because they've updated the back end. Additionally, our work at NIST, we run something called AM Bench. It's the additive manufacturing bench. It's a competition program that we run twice now. We've done in 2018 and 2022, and the next one's in 2025. And we have generated lots of different data on that one, data.nist.gov. If you search for additive manufacturing, or AM Bench, if you search for AM Bench, you'll see a lot of this precise measurements that we've taken about the additive manufacturing process. The goal behind this effort was to provide a platform for validating additive manufacturing models. And so when we see different models that are developed, predictive models, that's very much something that's very volatile, right? Depending on the material, depending on the laser. So the goal was to say that this is a part that we're manufacturing. These are the parameters that we're going to use, and challenge folks to give us what the results are going to be. And so all the data that's used in order to develop and to validate those models, it's all available on the internet as well.
Great, very appreciated.
I was going to just add that at ASTM we run a Center of Excellence for generating, basically taking research that generates standards, and part of that ecosystem we have a CMDS, Committee for Material Data for Standards, and so we have dozens of companies and organizations from around the world who are contributing data to that, and from that data then you can basically set things like design allowables in a standard, because you have enough different companies with different machines and or different powder lots contributing. I don't know if we make that data itself public. No, it's because the data itself is proprietary, but we use that data then to inform standards. And if people are contributing to that, I think within that maybe they should share it with each other. So your best bet is join the CMDS, get access to the data, because you're contributing data to. So I think that's sort of a fair way. Is if you contribute, you can get access. So.
Thank you. Sure. Yeah, ASTM and other standards associations can really help the universities and industries to make a unique language. As you know, for DED we have more than 10 terminologies. Every paper uses its own terminology. So I think standards for terminologies, for the qualification, for especially when we started to work in our project, we found that we don't have acceptance criteria. So I found the madam worked in the PORS acceptance criteria. It was really nice work. So because to find a defect, to identify whether this is acceptable or not acceptable, we need acceptance criteria, and standard can help us.
So you want to be a moderator for this discussion? I think you gave a lot of very important issues in this regard.
And I was going to say on the acceptance criteria issue, acceptance criteria is dependent upon the criticality of the risk. So if there's very little risk for a failure, then you can accept a lot of defects. If there's a high risk, then you can't accept very much. And so ASTM has come out recently with a criticality standard for aerospace components. And so from there you can start to create acceptance criteria. We do have standards for all of the terminology that you're talking about. The problem is some people just ignore them and write whatever they want anyways, because standards are not legally binding, right? They're consensus. And so unless people, some countries, they make them legally binding for certain reasons, but not journal articles, right? So you can say whatever you want. And it's up to people who are editors to make sure that people follow the standards. So not much we can do about that.
So how far have we been improving this issue in terms of standardization and the training? Because in the Korea we have dozens of powder manufacturers as well as equipment manufacturers, but the quality is different, and level of the technicians skill is different. Also the machine that we have, actually I have a new graduate student and let them train through the equipment manufacturer, and then I asked him to give it a try, and then every day he didn't work out, it doesn't work out, it didn't work, something like. And then how you can scope this issue? So do I have to wait until my students get skilled, or just so there should be some sort of not just specific manufacturer, not specific powder manufacturer or equipment manufacturer oriented, but somehow standardize the method from the scratch. I think that is one of the purpose for the ASA International Study. So
yes, so when it comes to operator training and certification, we already have standards. So there are a series of standards, ISO ASTM 52926, 1, 2, 3 up to 5. It covers requirements for operators for laser powered fusion, for DED, and for BJT. So standards are already published. So you can refer the standards, and in that standard very clearly it says what you need to know and how you get certified against those standards. And particularly for aerospace application, there's a standard called ISO ASTM 52942, very clearly talking about the requirements for an operator in operating a laser powered fusion machine. But the only caveat here is that it is tied up to a specific machine model and a material group. It's primarily because all these different machines have different architecture. So if you're certified in a specific machine model, that certification cannot be transferred to another machine model. So that's specifically for the 52942 standard. But for 52926, it is agnostic. Hope that answers the question. Yeah, these standards are published right now, so you can follow that particular standard. As I said, the 52926 series, that's the standard that you can follow. And in that standard, it clearly says what kind of knowledge an operator should have in operating these different technologies. So it's again a chicken and egg problem. So it comes from the end user. For example, if an OEM says that whoever is producing a part for me, he should be qualified against this particular standard or against this particular requirement.
I think you raise a good question. It's something that for people to enforce these standards, then they need to. Standards are, unless they're legally binding for some reason, then the only reason people use them is for contractual reasons. So if people buy a part and say, well, we want you to create those parts through this standard methodology with a certified operator who's been trained according to the standard, as long as the buyers require that, the service providers, parts sellers will do that. But until the buyer requires it, then people won't necessarily use that kind of training. I think it takes a little bit of time. I think what you're finding is people are finally realizing that training's there, and the various machine manufacturers are offering ASTM certified training, and so now people will go out and hire, put that on a list of skills that they want them to have. It just takes time. And when we started the standards committee in 2009, like that was 15 years ago, we now have 70 standards that are ASTM ISO standards. There's others. It's taken time. We still probably need another 150, 200 standards to really get to where we need to go. But I feel encouraged by the recent progress. It's actually accelerated quite a bit recently.
So how about training students in the academia? So any of you can give.
Well, I just wanted to add a couple things. So out of those 70 standards or so, in ASTM ISO, there's maybe 8 or 10 standards right now on qualification. And there, you look in terms of where is a lot of the standardization activity right now in ASTM and ISO, and a big chunk of it is on qualification. So there's a bunch of qualification standards in progress, so they're being worked on, written, etc. So over the next 3 to 5 years, I'd expect that number to at least double. And the other thing I'll add, because you mentioned training, you just talked about training, ASTM does offer certification training courses. And so you can become an ASTM certified operator and get standards against that, as these guys have said. So there's a lot of activity, and there will be a lot more coming.
How about training students in the academia? So you get the graduate student, and how is it working?
Academia. So, well, usually when we get a new machine, we get some of the technicians trained on the machine, so they become the expert users, or some of the research scientists to get trained on it, and then they become the ones who train the PhD students on using the machines. But then after potentially 3 or 4 years of operating the machines, they become as expert as the person who trained them at start. But we don't have a standardized process, if I can say so, at university.
It's a typical problem on the university environment, right? We may have money to buy a new machine, but we may not have money to hire a new technician to support the machine. The good news is at Louisiana State University, we set up so-called user centers. That means those centers can provide a service to the whole campus, so they can collect a fee. In my mechanical engineering workshop, we have a center provide a service to the entire campus, to even to people outside of the university. They pay a fee hourly rated based on the material they use, based on number of hours of laser powder bed fusion machine usage. The center will charge users. With the revenue generated from those kind of services, basically we have money to support more technicians. I feel technicians are really important. They can stay in that job over a long period of time. And unlike a PhD student, the PhD student will spend, let's say, several years to get them trained, and then they are going to graduate and leave. And that means we have to start the process again and again every few years. And another thing you can consider is try to make your group really large, not just your own group. You can work with your colleagues, people with the same interests, get students working together, and they can learn from each other. So the group size is an important factor. I assume, I don't know what's the structure here in US, the group size is based on the amount of funding we can bring in to support them. And generally speaking, you need to convince your boss in the department or in the college to fund a few positions as technicians.
I was just going to add one point on the academia side in terms of, obviously we train graduate students, but also, and we have facilities, for example, at Penn State where we have technicians that will help us fabricate things, or else graduate students will get trained as needed. But we have also an additive manufacturing and design graduate program, which I direct, which is an avenue for people primarily in industry or the Department of Defense, for example, to earn their master's degree or certificate in additive manufacturing and design. And that allows them hopefully to be able to identify, it's a very multidisciplinary degree. It allows them to identify other places to sort of inject additive manufacturing in their particular industry, as well as to hopefully advance additive manufacturing further.
Right.
So when it comes to training, as professors mentioned, in most of the universities, you have additive manufacturing programs. But all these additive manufacturing programs are graduate programs, meaning it takes 4 years for you to come out, or you take 2 years to come out. So when you look at the industry requirement, they need people immediately. So what ASTM is doing in this case is to bridge that gap. So meaning the training that ASTM is offering is primarily short trainings, like 2 days or 3 days or 4 days kind of training to bridge the gap between what you learn theoretically in the university and what you're going to implement from an industry perspective. And another way ASTM is collaborating with different universities is that although you have an additive manufacturing program, but there are some micro modules which we are missing, in fact, that is related to the industry, for example, on standardization, on qualification, certification. So we work with universities to impart micro credentials as part of your bigger certificate course or the certification program. So this is how we try to bridge the gap from a high level education and workforce development perspective.
I'm personally interested in, so if you see our title, this is AM for space aerospace applications. I want to listen to your opinion. Thought there would be any challenges or new opportunities for space exploration in terms of manufacturing. Especially, I think in space environment is quite different from our environment here. So, do you think what kind of challenges we may have, what kind of new opportunities we would have in terms of 3D printing in space environment?
I'll start with just a real quick one. When one or two of the speakers mentioned turbine blades, single crystal turbine blades. Well, it turns out if you don't have gravity, it's easier to grow single crystal turbine blades. So if you're looking for a market that potentially is one that could benefit from space manufacturing.
It's interesting because I sat on my first panel for NASA, I think it was in the 90s, on that exact issue. Like what should we be doing to do fabrication in space or on the moon or on Mars or whatever? And at the time, they spent a whole bunch of time and money then on electron beam DED because, oh, well, we got a lot of vacuum out there and electrons are great. Well, it didn't really, it was an interesting problem, but it didn't necessarily solve a problem that they had right then. But I think what's the whole area of space has similar to actually the needs of the military with quick repair. And And so there's a lot of money being spent right now and a lot of really interesting things going around the world, partly because of what's happened in Russia and Ukraine, making it very real. Like, we have to be able to fix stuff. I was at a European defense meeting where we were setting up in an area about the size of this auditorium. They had generators, they had all kinds of metal machines, polymer machines, they had equipment that was broken, and they were repairing it and trying it right there. And I think that is going to get applied in space because it's a little bit easier to try it here. We've already got some stuff up in space, but the other thing I think that's driving it, frankly, is this whole new space area, and some of the world's most wealthy people want to go to Mars and they're spending a massive amount of money to generate a whole new space industry. So I think finally, after like talking about this for 25 years, it's probably going to start happening soon, I guess, is partly what, because of the combination of ultra wealthy people in the new space industry combined with the DoD expeditionary force, full-time affair type problems. I don't know if it,
So in space, in the field of space, there are companies now that are already using parts, printing components, flying around. So Thales Alenia Space, they have a lot of products already, especially for satellite components. Obviously, there are lots of parts I've seen them also being made by SpaceX and others that rely not just on development, but also as real. And it's a great technique from the point of view that you don't need a mass production for that. You need only a few custom components. So I can see additives spreading quite nicely in the field of space, but at the same time, the other problem is that, of course, it's not mass production again. You're making only a few pieces here and there, and that's why the application remains quite niche from that point of view.
All right. I think if I'm allowed, maybe to follow this answer, your comments and your advices. So I think another issue would be material issues. So if in space environment, maybe we cannot find all the metals or all the elements we can easily find on the Earth. So do you have any comments? Like, so do you need any new material? Can you use new materials for 3D printing in space environments? So any thought about that?
Yeah, I've seen a number of studies going on out there where you're doing like Mars regolith or Moon regolith type stuff, where they've been able to melt it, portions of it, not creating something that has really good fatigue properties. But I think using the materials there, I've seen more people do things that are powder based or even concrete based. For we're taking that as a filler and we're bringing some sort of binder or something else to use it to create bulky structures, because we don't want to bring a lot of material to make a bulky structure like a habitation or something like that. And I've seen some really good work being done in that area. As far as work being done to actually break down the components of Moon and Mars into its constituent alloy, elements in an alloy from there, I don't know that I've really seen people work on that problem.
Well, I've seen some work on that in Loughborough University. They were trying to work on simulated moon regolith, so essentially the dust of the moon, and they're trying to use a binder-based technique, which was then, I think, was proposed by ESA as the design for the moon lander. They call it the moon base or something like that. But I think one challenge for the space sector, and also a challenge for many other sectors, as you may have seen today when I spoke about fusion, is the availability of materials itself. So many of the thrusters used in space applications rely on materials like platinum alloys, platinum rhodium alloys, again, very expensive materials. Niobium, for instance, which is mostly mined in very limited locations in Brazil or in China. Same for fusion, vanadium, how much vanadium we need to get nuclear fusion up and running, and it's mostly mined in very limited locations, and it's affected so much with the socio-political climate in the world. So I think that we're gonna come at some point under quite significant pressures for not being sustainable enough when it comes to the use and choice of materials for our applications, when we find that to make a thruster, we don't have the material we want to use for it.
So I think it's good enough panel discussion for today. I guess some of you have already jet lag, and I think stuff is done in the evening. So thank you very much for active participation in your presentation at this BrainLink FF Talk concert. And the audiences, thank you very much for attending this conference. So we are going to end this talk show. Thank you.